In this lecture,
All right. Good morning. Good morning, and welcome back. So I just had a fat uh breakfast. Yeah, I just had a fat breakfast. So hopefully that's gonna give us enough strength to um work until like to study until probably at 5 until 5. Of course, you're gonna have breaks. I'm gonna have lunch between the days. I mean, during the day. So we're starting at 9 o'clock. Okay, we're gonna have the next break at 1. I mean, at 7. Okay,
you'll learn how
let's
to
just
use the
dive deep
Anki
into it.
flashcards, which are included in the course. The point of the flashcards is to test your understanding and memory of all the topics that we are going to be learning about in the course. We use Anki software for the flashcards. That is spaced repetition software, and what it is designed to do is to make sure that you've got good understanding and memory of all the topics of the course and that you develop that as quickly as possible. The way it works is you will see a flashcard with a question on one side of the card. And then if you answer that question correctly, then you're not going to see that card again for a little while. However, if you're not able to answer it correctly, then you're going to see that card more frequently until you've got that information really well memorized. So, because you're going to see any topics that you're not as clear on more frequently, this is going to give you a really quick understanding, quick memory of all the topics that are going to be covered. You'll see exactly how the software works as I show you it in this lecture. But the first thing that we need to do is to download the software. So you can see here I am in Google and I have searched for Anki download. And I'm going to click on the first result here, which is at apps.ankiweb.net. So I click on that, and then if you click on the download button, you can see here that you've got the different options. You can choose Windows, Mac, Linux, or iPhone or Android. The desktop version, so for Windows, Mac, and Linux, they are all free. The mobile version you do have to pay a fee for. So you can use these for free on your desktop, but if you're going to be commuting from work or school, for example, on a bus or a train every day, then it is worth getting the mobile version so that you can make the most of your commuting time. Okay, I'm showing you how to install it on a Windows desktop here. So I'm going to choose the Windows version and I'm going to click on the latest stable release. So I will click on that and then that's going to download it to my downloads folder. I'll just give that a second to complete. And once it's done, I can click on the installation file. It's a really simple installation. I just basically click on install and accept all the defaults in here. This will take a minute or so to install. Then I can click close when it's done. This is going to put a shortcut on my desktop. I'm going to run it from the taskbar down here. So I'll search for Anki and then I'm going to open the application and then I'll accept the English United States is fine for me. I click OK for that and then yes to
I have it on
confirm.
right now.
And
I have it
that's
on right
the
now, but
software installed. The
it's
next
not
thing that I
showing.
need to do
So
is
let me
to
just
add
do
the course flashcards here.
uh
So we need to download those
set.
first. So you can
All right.
see in
So that's how
the
it
course
looks
here
like.
that the flashcards are downloadable from inside this lecture. So download the flashcards and then we're going to install them into the Anki software.
Okay.
So I've already done
So
it on my PC
oh
here. I've already got the flashcards downloaded to my downloads folder. But they're in a zip file, so I need to unzip them
hold on
first.
1 second, close
So
this and
I
then I'll
will
go.
go
Okay.
to Windows
All right, so I
Explorer
can close
into my
this.
downloads folder. There is the zip file. So I'm going to right click those first. So you can see in the course here that the flashcards are downloadable from inside this lecture.
Let me
So
see your notes.
download the flashcards and
Okay,
then
so
we're
it's
going
not
to
in notes,
install
so
them
I will
into the Anki software.
hold on. Okay, so the flashcards, I guess they will be specific on the specific sections. It won't be on all sections. Okay. All right.
So I've already done it on my PC here. I've already got
Oh,
the flashcards
so this is how it
downloaded to
looks
my
like.
downloads folder. They're in a zip file, so I need to unzip them first. So I
I'm
will
gonna
go
do
to
English.
Windows Explorer,
Are you
into my downloads
sure?
folder. There
Yes.
is the zip file. So I'm going to right
Okay,
click
so this is
on
how it
that
looks
and I'm going
like.
to extract here.
It looks like it's
And then that will
something that
extract
you
an
can just build
APKG
by
file.
yourself.
This is
You know what
what
I'm
I'm
saying?
going to
Like
import
you can
into the
probably build
Anki
this with
software.
Google,
So now I can go back
not
to the
Google,
Anki software
with a
and I'm going to
Flask
go File
with
and
Python,
Import.
basically.
And then I'm going to browse to my downloads folder and I am going to import that file that I just extracted. So I click on that
Can
and then I can just click
import,
on close on the
switch
information box here. And
profiles.
now I can see that those flashcards are available inside
So I don't have
Anki. And if I
any right
expand
now.
this out,
So
you can see that there are separate flashcards for every single section.
okay,
So what to do as you're going through the course is start doing the flashcards for that particular section. The actual course topics start
okay.
in
Let me
section
open the
3.
actual.
So if I've just completed section 3 of the course, I would go and I would double click on section 3 to run those flashcards. So I will double click on that and then I can click on study now.
Yep,
This is going to
it's
start
used.
asking
Yeah,
me
it's using
questions.
Python.
There's
It's
usually
made with
20
Python.
questions for each section. So
I
this
thought
is
so.
the first
You know, I
flashcard.
once
So I
tried
read
Python,
what it
and
says
that's the
here,
way that you
and then I think
kind of
what
looks
the
like this
answer
when
is.
you're
I then click
creating
on
like
show
a
answer,
a
and
GUI
if I got the
application.
answer correct, then I'm going to click
All
on
right.
either hard or good. So if that was a easy enough question, I can click on good. If I had to think about it a bit, then I can click on hard. If I get the question wrong, then click on again. There is also easy if it was a really easy question. You know, you've got that memorized, you don't need to see it very often. I've done that first one. Let's say I found that easy enough, so I'll click on good. I then get the next question. This is a fill in the blank, so I have to say what the top layer of the OSI model is. That would be application. I click on show answer. I got that correct without having to think too much, so I can click on good again. And then I get the next question. Again, think what the answer is, click on show answer, and then click on the button here, depending on if you got it wrong, click again, or hard or good, depending on how easily you got that correct. When you go through the cards for the first time, each new card, you're going to have to answer that correctly twice. So this is building your memory for each of those questions. And you can see in here how long it's going to be until you see that flashcard again. As you go on to the next day, you'll see that the interval between seeing the card again is going to get longer and longer. So on the first day, you see right now, I'm going to see it in under 10 minutes. If I see that same flashcard twice and I click on good 2 times, then this will change to 1 day and I won't see that flashcard again until tomorrow. So what happens as you're going through this is, as with flashcards, if it's quite easy for you, you're not going to see that card again for maybe several days. If you found it more difficult, then you'll see the card again the same day, and you're going to see it more frequently moving forward as well. Once you've got that card memorized and you're clicking to indicate that, then you're going to see it less regularly. So what happens is the flashcards, the questions that you find easy, you're going to see them not so often. Anything that you're finding harder, you're going to see it more regularly until you've got that really memorized. When you've finished all the cards for the day and you don't have any left due until tomorrow, then you'll see this message saying, congratulations, you have finished this deck for now. So that's you done for the day. You can come back to Anki again tomorrow and do more review cards again. And to make the best use of the cards, it's recommended that you use them every day. By using them every day, you're going to see the information regularly, and that's really going to put it
Okay.
into your long term memory.
So
So when you do the
alongside this, I'll
actual
probably
exam,
create
you're going to be ready for the questions that you're going
another
to get
one for
on
our
exam day. one last recommendation for you
What are they
is,
called?
as you go through the course and you're completing new sections, is to drag and drop the
Our
flashcards for those sections into section 3 in Anki.
um
So, for example, let's say that you have just
Linux
completed section 4. What
commands.
in the course, what to do is to click on section 4 in
Can't
Anki
find
and drop it onto
what I was
section
looking
3.
for.
What does is it then merges sections 3 and 4 together in Anki. So now when I go and double click on section 3, I'm going to get questions for section 3 and for section 4. So that means that I'm going to be studying the questions for all the sections that I have already done. And then once you have completed section 5, you would also drag and drop section 5 onto section 3 as well. That will add the section 5 questions into your merged deck. So now you'll be getting review questions for 3, 4, and 5. By doing it that way, it's a lot easier than trying to do it individual section by section in Anki. Okay, that was everything that I needed to tell you here. See you in the next lecture.
I think saving is the only way. Yeah.
In this section, you'll learn about the OSI reference model. The OSI model is a conceptual framework that helps lay out how computer networking protocols should work with each other. And it really helps aid your understanding as you're learning about networking as well. Actually, this is going to form the bedrock of your understanding of networking, so it's a really important section. We'll also go into the definitions of the different layers that make up the OSI model before covering them in much more detail in later sections throughout the course. We'll also cover the TCP/IP suite and discuss how it relates to the different layers of the OSI model. In this lesson, I'm going to give you a very basic introduction to networking. If you already know about switches and routers and network topology, you can just skip right on ahead to the next lesson. But if you're brand new to networking, then I'm going to give you a quick overview here. So let's say that we've got an office which is in New York for our company. In that office, I'm going to have end hosts like PCs, a server, and a printer, like you can see here, and they're going to need to be able to communicate with each other. So for that, I'm going to put in a network switch, and I'm going to cable my devices to that switch with Ethernet cables. And that's what a switch looks like. There's a Cisco switch. You can see it's got a lot of ports in there so that I'm going to be able to connect in a lot of devices. The switch is what allows connectivity on my local area network. In that office in New York, maybe I've also got a laptop which is going to connect in over a wireless network. So for that, I'm also going to have a wireless access point which is also going to connect into our switch. And that's what a wireless access point looks like. So I've got all my devices in New York now. They can all talk to each other. I've built a local area network. A local area network is a network that connects devices which are in the same local area, like in a single office or maybe a university campus. Okay, I don't just want my end hosts in my office to be able to talk to each other. They're going to want to communicate with other devices out on the internet as well. So for connectivity out there, I'm going to need a bit more of an advanced device, which is built a local area network. A local area network is a network that connects devices which are in the same local area, like in a single office or maybe a university campus. Okay, I don't just want my end hosts in my office to be able to talk to each other. They're going to want to communicate with other devices out on the internet as well. So for connectivity out there, I'm going to need a bit more of an advanced device, which is a router. A router is able to make advanced routing decisions to route traffic between different areas of your server and a printer, like you can see here, and they're going to need to be able to communicate with each other. So for that, I'm going to put in a network switch, and I'm going to cable my devices to that switch with Ethernet cables. And that's what a switch looks like. There's a Cisco switch. You can see it's got a lot of ports in there so that I'm going to be able to connect in a lot of devices. The switch is what allows connectivity on my local area network. In that office in New York, maybe I've also got a laptop which is going to connect in over a wireless network. So for that, I'm also going to have a wireless access point which is also going to connect into our switch. And that's what a wireless access point looks like. So I've got all my devices in New York now. They can all talk to each other. I've built a local area network. A local area network is a network that connects devices which are in the same local area, like in a single office or maybe a university campus. Okay, I don't just want my end hosts in my office to be able to talk to each other. They're going to want to communicate with other devices out on the internet as well. So for connectivity out there, I'm going to need a bit more of an advanced device, which is a router. A router is able to make advanced routing decisions to route traffic between different areas of your network. That's why it's called a router. And this is what a router looks like. You can see it's pretty similar to a switch, same kind of size. Typically it will have less physical ports on there, and it will support different types of ports so that it can connect different types of networks as well. Next thing, we know that there's going to be bad guys out on the internet, hackers who are going to try to attack us, so we need to guard against that, so we're going to put a firewall in place. And this is what a firewall looks like. Again, you'll see that our different network devices tend to look very similar to each other, but they fulfill different tasks on the network. The firewall secures the different parts of our network from each other. Okay, so that was our New York office, the local area network, and its connectivity out to the internet. In a larger company, we're not going to just have one office in New York. In our example here, let's say we've also got an office in Boston as well. In Boston, we're going to have a similar kind of setup, the same kind of devices in there. We're going to have the local area network in Boston. And we've also got local connectivity to the internet from Boston as well. Now, because we're the same company, I'm going to want to have connectivity between my New York and my Boston offices. I want the end hosts in both of those sites to be able to communicate with each other. It is possible that they could communicate securely over the internet if I set that up, but another way of doing it is I could maybe put in a dedicated connection between my two routers in both sites, and that's going to give me my wide area network connection between my different offices. Okay, so that's a really quick overview of networking. And the point of networking is to allow that connectivity between our different end hosts on the network. So looking now at the characteristics of a network, we've got the topology. If I just go back to that previous slide, this is an example of a network topology diagram. The
Don't judge my
topology
notes.
is how
I'm
the
gonna update them
devices
soon.
are connected up to each other.
But
Other
that's how I mostly take
characteristics
notes.
is the speed of the network. Typically, the faster the network is, the more it's going to cost you. And cost is itself a characteristic as well. Things that will affect the cost are the type of devices you have in there, the size of the network, the different technologies you're using, etc. Other characteristics are security. I mentioned the firewall in the previous slide. We're not going to just have security on our firewall though. We'll also have security features on our routers and on our switches, and we can have other security devices such as intrusion prevention systems as well. Next, we have availability. We're going to want to make sure that our network always stays up. And for mission critical components in the network, Typically, we don't want any single points of failure, so we will double up on those components so that if any one fails, we've got an alternative component that will still be up and running. Scalability is also important. We want to design the network in such a way that it's easy for it to grow with our company without requiring a redesign. And reliability, similar to availability, where we want to make sure, again, that the network is going to be reliable, but it's going to continue to work. In this lesson, you'll learn about the OSI model. The Open Systems Interconnect model is a standard of the International Organization for Standardization, so it's an ISO standard. It's a general purpose framework that characterizes and standardizes how computers communicate with one another over a network. So the OSI model, it's conceptual. It's not a physical thing or an actual protocol or technology. Its 7-layer approach to data transmission divides the operations into specific related groups of actions at each individual layer, and a layer serves the layer above it and is served by the layer below it. Now, I know that doesn't make much sense yet, so let's have a look at how this works in action. So let's look at an example. Here I've got a sender on the left, let's say that's my laptop, and we've got a receiver on the right, let's say that's my email server, and we're both connected into a switch. And I'm going to send an email to my email section for standardization, so it's an ISO standard. It's a general purpose framework that characterizes and standardizes how computers communicate with one another over a network. So the OSI model, it's conceptual. It's not a physical thing or an actual protocol or technology. Its 7-layer approach to data transmission divides the operations into specific related groups of actions at each individual layer, and a layer serves the layer above it and is served by the layer below it. Now, I know that doesn't make much sense yet, so let's have a look at how this works in action. So let's look at an example. Here I've got a sender on the left, let's say that's my laptop, and we've got a receiver on the right, let's say that's my email server, and we're both connected into a switch. And I'm going to send an email to my email server. So obviously the sender is going to compose this traffic that's going to be sent to the receiver. And as it builds this packet that is going to be sent, it's going to start off at the top level and then it's going to work its way down to the bottom level. So at the sender, first off, it will create the layer 7 information, which is the application layer. So if I'm sending an email, that will contain information such as the from and the to field, etc. Then it will encapsulate the layer 7 information in the layer 6 information. Layer 6 is the presentation layer. And then it will encapsulate that in the layer 5 session layer information. Layers 5, 6, and 7 are known as the upper layers, and they're more important for application developers rather than network engineers. Network engineers start to get really interested when we get down to layer 4. So we've got our upper layer traffic composed. That then gets encapsulated with our layer 4 header, which is the transport layer. At layer 4, this is going to be either TCP or UDP, and it will include the port number, such as port 80. It's web traffic, port 25 for our email example. Now, if you don't already know the details of TCP, UDP, and port numbers, don't worry about it yet. We're going to cover all this information in much greater detail in later lessons and actually throughout the entire course. Okay, next thing that happens is that will then be encapsulated with our layer 3 header. Layer 3 is the network layer. And important information that is included there is the source and destination IP address. A network device that operates at layer 3 is our routers. The next thing that will happen as we compose the packet is the sender will then encapsulate that information in the layer 2 header. Layer 2 is the data link layer. And important information there is the MAC address if we're sending this over an Ethernet network. The network device that works at layer 2 is our switch. And finally, this packet is now ready that we can actually transmit it over the wire. When we do that, we're down to layer 1, which is the physical layer. A network device, which you don't really see anymore, which operated at layer 1 was hubs. So we've now composed the packet at the sender side. We've put it onto the wire, it's going to travel over the network, and it's going to reach our receiver. The order of operations is going to be reversed now, because obviously it comes in at the physical layer. The receiver will process the packet from the bottom layer back up to the top layer now. So it comes in at the physical layer. The receiver will then look at the outside header, which is the layer 2 header, and it will check that this packet is for it. It will check that the destination MAC address in the layer 2 header is its MAC address. If it's not for it, it will just discard the packet. Next up, it will continue with de-encapsulation now. It will then look at the layer 3 header. It will check the destination IP address, and again, it will check that the packet is for it. If not, it will discard the packet. Then we carry on with our de-encapsulation on the receiver. It will look at the layer 4 header. What this is useful for is, imagine the receiver is not just onto the wire, it's going to travel over the network and it's going to reach our receiver. The order of operations is going to be reversed now, because obviously it comes in at the physical layer. The receiver will process the packet from the bottom layer back up to the top layer now. So it comes in at the physical layer. The receiver will then look at the outside header, which is the layer 2 header, and it will check that this packet is for it. It will check that the destination MAC address in the layer 2 header is its MAC address. If it's not for it, it will just discard the packet. Next up, it will continue with de-encapsulation now. It will then look at the layer 3 header. It will check the destination IP address, and again it will check that the packet is for it. If not, it will discard the packet. Then we carry on with our de-encapsulation on the receiver. It will look at the layer 4 header. What this is useful for is, imagine the receiver is not just an email server listening on port 25 for email traffic. Let's say it's also a web server as well, listening on port 80 for web traffic. Well, how does it know if this traffic is for its email server application or its web server application? It can tell by looking at the port number. Next, we will carry on with the de-encapsulation. We'll strip off the layer 4 header. We'll look at the layer 5 header at the session layer. We'll carry on up. We'll then look at the layer 6 header and then the layer 7 header. So that's the whole thing. That's how we got traffic from the sender to the receiver. Network. The network device that works at layer 2 is our switch. And finally, that's the whole thing. That's how we got traffic from the sender to the receiver as far as the OSI model is concerned. At the sender side, again, we start off at the top layer, we work our way down to the physical layer, it goes across the physical layer, it will hit the receiver there, and it will then de-encapsulate going in the opposite direction, going from the bottom layer up to the top layer. Looking at the benefits we get from the OSI model, engineers don't need to design a technology to work end to end from top to bottom of the model. They can just focus on their layer of expertise and make sure that they comply with the standards for the layers above and below. This leads to open standards and multi-vendor interoperability. For example, if you're an application developer, you can just focus on the top 3 layers. The lower layers are the domain of network engineers, so you don't need to understand them, you just need to make sure that where you interface between layer 5 and layer 4, you're complying with the standards there. Troubleshooting is also easier because you can analyze a problem in a logical fashion layer by layer. It's difficult to overstate just how important the OSI model is to computer networking. As you become more experienced with networking, you'll think according to the OSI model when you're troubleshooting or learning a new network technology. This will be natural for you. This is what I do really every day on a day-to-day basis. And on the job, you'll hear technologies and problems being described according to their OSI layer. For example, if you're troubleshooting a problem and you start looking at it in an overly complicated way, it might turn out that it was just because the cable was unplugged. And you would say to the guy next to you, oh yeah, it was a layer 1 problem. You might also hear of a layer 8 problem. That's when a user has made a mistake. Okay, this is going to be tested heavily on the exam, and like I just said in the last slide, it's really important anyway, not just for exam purposes. For your whole understanding of networking, you really need to know the OSI model. It's going to help you. So we are going to have acronyms that are going to help us remember what the actual names of the different layers are. The classic acronym that you'll see in all the books going back years and years is please do not throw sausage pizza away. So again, the layers were the physical layer, then the data link, then the network, then the transport, the session, the presentation, and the application layer. When you're first beginning, in fact, to be honest with you, I still remember it from the acronym, and it's just automatic for me. I know it's please do not throw sausage pizza away, and that helps me easily remember what the names of the different layers are and what order they come in. Other acronyms you can use if you don't like that one that's relevant to networking is please don't need those stupid packets anyway. Another one that would be relevant to us here is please do not teach students pointless acronyms. And a useful one, please do not take salespeople's advice. If you've been working in networking for any time already, you'll know that's great advice. And my personal favorite, please do not touch Superman's private area. Okay, I think enough said about that.
Yes, that's funny. So this will be please don't need those stupid packets anyway. So from the so that's please don't need those stupid packets anyways. Physical data. Okay. All right, so we can do this. I'm going to keep my tips down here. So that's physical data network. Forgot session. P is for forgot. Anyways, remember that. Okay, PD and it's whatever it is. We'll go to the next one.
In this lesson, you'll learn about the TCP/IP suite. TCP/IP was developed way back in the 1960s by the US Department of Defense's Advanced Research Projects Agency, that's DARPA. It's a protocol stack which consists of multiple protocols including TCP, which is the Transmission Control Protocol, and IP, which is the Internet Protocol. So it's not a single protocol, it's a protocol stack. What a protocol is, if you think of diplomats, when diplomats from different countries meet each other, there's a certain way that they're expected to behave and to communicate with each other. In computer networking, protocols basically mean the same thing. So if you've got two hosts and they're going to communicate with each other, there's going to be a protocol which is going to control how that communication should behave and how it should work. TCP/IP, it's the main protocol stack used in computer operations today. There used to be other competing protocols way back in the day, like IPX,
Department
SPX,
of
and Apple
War
Talk,
now.
but they're really dead now. TCP/IP is now ubiquitous. And whereas the OSI reference model is conceptual, the TCP/IP stack is actually used to transfer data in today's production networks. TCP/IP is also layered, but it doesn't use all of the OSI layers. though the layers are equivalent in operation and function. So it does actually use them, but in the documentation, it only lays out 4 different layers. Let's look at those now. So you can see on the slide here over on the left, IP, it's the main protocol stack used in computer operations today. There used to be other competing protocols way back in the day, like IPX, SPX, and AppleTalk, but they're really dead now. TCP/IP is now ubiquitous. And whereas the OSI reference model is conceptual, the TCP/IP stack is actually used to transfer data in today's production networks. TCP/IP is also layered, but it doesn't use all of the OSI layers, though the layers are equivalent in operation and function. So it does actually use them, but in the documentation, it only lays out 4 different layers. Let's look at those now. So you can see on the slide here over on the left, we've got the OSI model that we covered in the last lesson. So we've got the 7 layers there. Remember, the way to remember, easy way is please do not throw sausage pizza away. So we've got physical, data link, network, transport, session, presentation, and application. Over on the right, we've got the TCP/IP stack. So you can see we've only got 4 different layers there. Up at the top, we've got the application layer, which maps to all 3 of the application, presentation, and session layers in the OSI model. Below that, we've got the transport layer, which is a one-to-one mapping with the transport layer also in the OSI model. Underneath that, we've got the internet layer, which is equivalent to the network layer in the OSI model. And down at the bottom, we've got the link layer, which maps to the data link layer and the physical layer in the OSI model. Now, you know, I was saying in the last lesson, it's really important to understand the OSI model. The TCP/IP stack, for sure, if you're working in networking, you're going to know the different protocols like TCP and IP like the back of your hand. But when we're talking to other network engineers, it's more commonly the OSI model that we're going to be referencing. Moving on, looking at some host communications terminology. So when 2 hosts talk to each other, they're going to be exchanging PDUs, protocol data units. The PDU is the entire communication all the way from layer 7 down to layer 1 of the OSI stack. We can also divide that into different terms depending on which layer of the TCP/IP suite we're talking about. For communications up at the application layer, that's called data. For communications between the transport layer on 2 different hosts, that's called segments. Between the internet layer, those are our packets, and down at the link layer, those are our frames. So, you know, just on the last slide, I was saying typically real world, we're not going to be discussing the TCP/IP stack like this about the 4 layers. More commonly, we'll use the OSI 7 layers, but on this slide, the terminology actually is commonly used. So if I'm talking about layer 2 communications, I'll call that a frame. If I'm talking about layer 3, I'll call it a packet. And if I'm talking about layer 4, I will call it a segment. Another thing I need to tell you here is that Packet officially is at layer 3, but you might have heard me talking earlier on in this section and calling the communication between two hosts a packet. So really the correct term is a PDU, but in day-to-day conversation often we'll just call communications between two hosts a packet, meaning the entire stack. In this lesson, you'll learn about the TCP/IP suite. TCP/IP was developed way back in the 1970s. In this lecture, you'll learn about the upper layers of the OSI model. That's the upper three layers, 5, 6, and 7. Network engineers don't typically work directly with those upper three layers of the OSI model. They're more relevant to application developers, but we still need to know what they do. And for the exam, we need to know the definitions of each of the layers as well. It's quite likely that you'll be tested on that. So in this lecture, that's primarily what I'm going to be doing, is giving you the Cisco definitions so you'll be ready for the exam. Information included in the upper layers would include the message body and the subject line in an email message, for example. So let's look at the three top layers, starting with layer 7, the application layer. This provides network services to the applications of the end user. It differs from the other layers in that it does not provide services to any other OSI layer. The application layer establishes the availability of intended communication partners. Intended communication partners would be the host that this host is communicating with. If you remember from the lecture before when we were discussing the OSI model, you saw that straight line between two hosts at the same layer of the OSI stack. So the application layer establishes the availability of intended communication partners. That's that straight line going to the other host. It then synchronizes and establishes agreement on procedures for error recovery and control of data integrity. Data integrity means checking that data has not been altered or corrupted in transit. The next layer is layer 6, the presentation layer. This ensures that the information that is sent at the application layer of one system is readable by the application layer of another system. The presentation layer can translate among multiple data formats using a common format. For example, it might need to do this for computers with different encoding schemes. And the last layer of our upper layers is layer 5, the For example, it might need to do this for computers with different encoding schemes. And the last layer of our upper layers is layer 5, the session layer. This establishes, manages, and terminates sessions between two communicating hosts. The session layer also synchronizes dialogue between the presentation layer of the two hosts and manages their data exchange. For example, we might have web servers which have got many users that are using that web server. So in that case, we would have multiple incoming sessions. The session layer keeps track of all of those. It also offers efficient data transfer, class of service, which is similar to efficient data transfer, and exception reporting of upper layer problems. Okay, so that's the definitions of the upper layers. We'll go into the definitions of the bottom 4 layers in the next lecture. In this lecture, you'll learn about the bottom 4 OSI layers, where network engineers are not typically very concerned with the top 3 layers. We are very concerned with the bottom 4 layers. This is really bread and butter stuff for us. Each of these bottom 4 layers are so important that they're going to have their own dedicated section later on in the course. Here I'm going to focus on giving you the definitions which you're going to need to know for the exam. So the first of the bottom 4 layers, we'll start with layer 4, which is the transport layer. The main characteristics of this layer are whether TCP or UDP transport is going to be used and the port number. Now, if you don't know anything about TCP or UDP or port numbers already, don't worry about it too much for now, because we're going to be covering this in the dedicated section for layer 4 later. For now, you just need to know that if we want the communication between the two hosts to be reliable, then we'll use TCP. If speed is more important than reliability, like for voice or video traffic, then we'll use UDP instead. The other main characteristic at this layer is the port number. For example, port number 80 for HTTP web traffic, port number 25 for SMTP email. Now, there is quite a lot of other information also in the layer 4 header, but we'll talk about that when we get to that particular section in the course. The definition for layer 4, the transport layer defines services to segment, transfer, and reassemble the data for individual communications between the end devices. It breaks down large files into smaller segments that are less likely to incur transmission problems. The next layer is layer 3, the network layer. The most important information at the network layer is the source and destination IP address. Again, there's a lot of other information also carried in the layer 3 header, but we'll talk about that when we get to the later section. Routers are layer 3 devices. They operate at layer 3 of the OSI model. And the definition of the network layer, it provides connectivity and path selection between two host systems that may be located on geographically separated networks. The network layer is the layer that manages the connectivity of hosts by providing logical addressing. IP addressing is our logical addressing. Next layer is layer 2, the data link layer. The most important information here is the source and destination layer 2 address. Again, just like with layer 3 and 4, there is other information. Also included in the layer 2 header. For example, the source and destination MAC address if Ethernet is the layer 2 technology. Different layer 2 technologies use different formats for their addressing. For example, old legacy frame relay uses DLCI or DULCI numbers for the addressing. With Ethernet, which is what is always used on our local area networks, it's the MAC address that is used here. And switches operate at layer 2. Our switches are layer 2 aware devices. The definition for the data link layer, it defines how data is formatted for transmission and how access to the physical media is controlled. It also typically includes error detection and correction to ensure a reliable delivery of the data. And finally, we have layer 1, the physical layer. This concerns literally the physical components of the network, for example, the actual physical cables being used. Definition of the physical layer, it enables bit transmission, the ones and O's, between end devices. It defines specifications needed for activating, maintaining, and deactivating the physical link between end devices. For example, voltage levels, physical data rates, maximum transmission distances, and physical connectors, etc. Okay, so there you have it. That was the quick overview and mainly the definition of the bottom 4 layers. As we go through the
Okay. That was fast. My hands are starting to crumble. Okay. That was a lot of writing. That was a lot of writing. Way too much writing. Fast writing, as a matter of fact. This guy is, it's like he's talking on 2 times speed. Okay. So what we have next is we just need to ooh we in my opinion. Okay. I mean, we have like we have 5 more modules left. We got this. We're gonna finish this today. Finish this one today. I'm planning on finishing at least 2 today. That's like the final goal. At least finish 2 today. Okay, so I'm going to take a I'm going to take my notes over there. Um okay. I'm going to take my notes. Give me 1 second. Oh, okay, he's making his own game. We're just here grinding. Haven't even looked at the chat yet. I don't know if I have anybody here with me. Looks like I'm here by myself. It's all right though. All right. Okay, so let's take a note. Let's take some notes on front on the whiteboard over here. So let's transit to that. Okay, all right. Now, what have we learned so far? That typing too fast is not good for your hand. My hand is already hurting. Okay, all right. So, let's see which one is good. All right. Okay. So we have learned that there are 7 layers of network or the OSI model. Um, I'm gonna put it over here. I need more space. Okay, so OSI model, it has 7 layers. Which is 7 layers. The seventh layer is the application layer. Sixth layer is the data link layer. Sorry. As a matter of fact, I'm just gonna use my notes. Where are my notes? Okay. It's the presentation layer. I was wrong. Presentation layer. Presentation layer. Fifth layer, I thought was the session layer. And it is. All right. And then fourth must be the data link layer. And then third must be, what's third? Okay, the switch is on the network layer. Yes, yes it is. It's the network layer. Second layer is the network. Second layer is the protocol. No, it's the data link. Oh no, that was transport. Fourth layer is transport. Data link is the second. Okay, I might need to learn that. Okay, that's data link. That's transport. And then the first layer, which is physical. So the physical layer is our cables. I'm just gonna put it as simple as that. I'm just gonna remember it as the cables and connectors. That's it. Like, okay. Our data link layer, it's our Ethernet, close Ethernet MAC addresses and switches. Let's just go down here. So I'm going to fold out the transmitting access is controlled. Data detection. Okay, so here we have switches. Switches. On the network layer, we have what's on there? We have routers. Okay, better start learning the difference, my boy. Routers. On the transport layers, we have UDP transport is used. So that's like TCP/UDP transport and port number. So transport layers, port number, small segments, like transmission. So transport layers, port number, and UDP transport. UDP or TCP over IP. TCP transport port number. TCP transport. TCP transport requires port number. All right. On session layer, sessions layer establishes, manages, and terminates sessions between two communication hosts, synchronizes dialogue, operates efficient data transfer. So this data transfer and sessions management. Okay. Data transfer and session management. Okay, presentation uses information that is in at the application layer of one system. Variable application can translate among multiple data. Okay, so let's say translates data formats. Translates data formats with different. Okay. Translates data formats. Okay, and then we have the application layer, which just provides network services to the application of the user. Does not provide, establishes availability of internet communication partners, synchronizes and establishes agreements and procedures. So we can say it provides network services to the application user. So provides provides network services. Network services to the application. To the app, right? I can just say to the app, man. To the app. Okay, there we are. Yeah. So those are the OSI model. I also want to have I also want to have the TCP/IP model. So hold on, let me do some. I also want to have the TCP over an IP model. So TCP/IP suite. So we didn't really see what switches, routers. Okay. So for the TCP/IP stack. TCP/IP stack. OSI model. Okay. TCP/IP suite stack. All right, so we have the highest layer, which is application. Application, then transport, and internet, and then link. Okay, so we have application, transport, internet, and link. Internet link. Okay. Represents data, users, and codes, control, supports communication between and devices across diverse networks, provides logical addressing to servers. Okay. Segment, PDU, segment, data, segment, packets, right? Okay, so this is, say that's data, segment, packet, frame. And that is in between two applications. Is this PIP? Okay. Protocol doesn't system protocol. The main protocol stack is used to. Yeah, it's used to transfer data production network. Okay. Used to transfer data. Okay. Used to transfer data. Okay. So this is how it transfers data. So between application and application, transfers data, I guess. Link, that would be also a link. Internet, okay, and transport. I don't know how I'm going to make myself remember this. Okay, so between these two, line, link. You will call it a data application. It's hard to explain. And I just took the notes. Okay. When two hosts talk to each other, they will be using UDP. The name in between is what you use to refer to the specific layer. Talking about layer 3 of the segments communication. So this is layer 3. Okay, this is layer 3, layer 4, layer 2, layer 1. Only has 4 layers. Okay. Only has 4 layers compared to OSI model. Okay, all right. Okay, so those are the quick notes so far. What's the 7th layer? Okay, so let's just do the layers from up and down the outside. OSI model. The layers are physical. All right, physical, data link, network, transport, session, presentation, application. Application sessions. No, applications, presentations, sessions, transport, network, data link, physical, data link, transport. No, physical, data link, network, transport, session, session. After session is transport. It's presentation. Oh my gosh, I keep on forgetting presentation. After session is presentation and then application. Application, presentation, session, transport, network, data link, physical. I am still not remembering. I still haven't remembered. So physical, data link, network, transportation, session, presentation, and then application. Whew. I probably still do not have it yet. I don't know if I will have a pun or whatever it's called for that, but yeah, that's that. I believe there will be a okay. So let's go back and see what it's all about. You know what I'm saying? All right. Let's focus a little bit. Let's focus a little bit more on us. Okay. All right. So let's go back to our.
The rest of the course will be covering those in much more detail.
All right, our first assessment. Let's start. If a data has to be transferred with error checking and recovery option, okay, we will use UDP for that. I did not take notes for that. I did not take note of that. UDP, TCP. I had all for TCP. My gosh, I did not have anything for UDP. Okay, PDU. Hold on. Incorrect. It's incorrect. Oh my gosh. Okay, then it must be TCP. Oh my gosh. TCP, yeah. It's layer, but that's not. It's used to represent Okay, incorrect. YouTube does not provide reliable data transmission. Yeah. Hold on. I remember writing about that. Anyways, one network characteristics is directly related to the ability to add new devices without affecting current network reliability, scalability, I believe. Yeah. Scalability is about expanding and managing more devices. Okay, while OSI layer is responsible for data presentation, translation, such as encryption and compression. That's yeah. Okay. Presentation can long, including schemas. All right. So this is how I usually take notes with responsible. Back when I was in school, well, I'm still in school, but back when I was in school and I was taking courses like this is how I will take notes, because when you're practicing like this, right? When you get something wrong and then you write it down like that, so that presentation, translation, such as encryption and compression. All right. What type of devices operates in OCI network layer? Responsible for forwarding, It's a switch. It's a router. OCI network routers. Yeah. Routers. Responsible for forwarding data based on IP. Forwards data based on IP. Manages connectivity host. Yeah, whatever. I'm just gonna have it like that. What layer on SI model is responsible for encrypting data to further protect sensitive? I would think that's the data link layer. No, that's low layer. That's a really low layer. Oh no, that's for encrypting. What encryption? Will that be the presentation layer again? I don't think it's the network layer. Yeah, presentation. This is the presentation layer. Or is it transport layer? I forget a lot about the transport layer. Okay, let's see. Correct. Yep, encryption and decryption. Compression. And compression, such as encryption. Okay, it's an 80. Another 80% again. But we're going to take a note on what. Okay, so incorrect TCP. So if data has to be transferred with error checking recovery option, that's gonna be TCP. So let me write that. TCP provides use transfer protection of networks. Transfers data with error checking and recovery option. I'm just gonna add that. Okay, now we're back into. So now we're in module 4. That was
We've
slow
covered quite a bit of theory
and
already,
embarrassing,
so I'm
but
sure that by now
that's okay.
you're itching to see how to actually configure our Cisco devices, our routers, and our switches. Now, Cisco do have graphical.
Okay, I'm just gonna add a few more to the board. Just a few more. Oh man, because that's actually important. That's something important to know. Encryption, decryption. Right? Encryption. Encrypts. That's it. That's all I wanted to know. All right. We're back to you now.
User interfaces, like web-based interfaces that you can use to configure the devices, but in the real world, everybody uses the command line. Well, experienced engineers use the command line because it's
I forgot to. Honestly, sorry. I feel like I don't need all of these. Like, wish that I could hide them. I feel like all of these things are unnecessary, really. But hey, it is what it is. So
much quicker than using the GUIs. And the operating system that is used on enterprise grade Cisco devices is iOS. So in this section, you'll learn how to connect to the router or the switch, and then how to make your way around the command line. Just before we get into that, we're going to have one more theory lecture where I'll talk about the different operating systems that are available from Cisco, because there's not just iOS. So we'll do that first, and then we'll get into actually how to connect to the device and how to make your way around the CLI. Let's do that now. In this lecture, you'll learn about the different operating systems that run on Cisco's different router and switch platforms. Now, you don't actually need to know this for the exam. The exam focuses purely on iOS, on Cisco routers and switches. So if you're wondering why am I including this then, the reason is that it's something that you would wonder about anyway, and I want to explain to you that by taking this course and learning how to configure Cisco iOS, it's going to enable you to work on any of the different Cisco routers and switches, because from a management and an administrative point of view, it's pretty much identical no matter which actual operating system you're working on. So I'll start off by giving you a bit of history. Many people think of Cisco as being a routing and switching company, but they actually were just a purely routing company when they started off. And when they did start off, iOS was the original operating built by Cisco, who are the biggest network upgrades in the time since the Catalyst operating system. Now, both the Catalyst switches and originally the PIX firewalls, it's now the ASA firewall, were ported over structure operating systems. Let's look at those now. So on the Cisco Nexus and the MDS data center switches, they run on NXOS. On the high-end service provider routers, the NCS and the CRS, and also on the ASR9K and the XR12K routers, they run on iOS XR. And on the ASR1K service provider routers, they run on iOS XE. So you're maybe thinking, oh, well, this is going to make things more difficult if there's all these different operating systems, but really it doesn't, because all of the different Cisco operating systems, they are incredibly similar from the command line point of view. If you know a command in iOS, it's probably going to be exactly the same command on all of the different operating systems as well. As far as administering and managing them, they're all nearly exactly the same. So you're maybe wondering, well, if managing them is exactly the same, why is there the different operating systems? The main reason and where they're different is under the hood. iOS has got a monolithic kernel, meaning that if one process running on the router crashes, it can crash the entire router. The other newer operating systems have got microkernels, and the processes run in separate protected memory address space. So if one of the processes crashes, it shouldn't affect the running on the rest of the system. Built by Cisco, who are the biggest networking company in the world, to run on enterprise grade routers and switches. So it is very hard.
We do not need much of that.
In this lecture, you'll learn how to connect to the command line on Cisco routers and switches over the corporate network. Before we get started, I want to make it clear that the way that the lab exercises work in this course is different than connecting to real routers and switches. The lab exercises use the free Cisco Packet Tracer software, which is standalone software that runs on your PC. So when you're doing the lab exercises in the course, you're not connecting to real routers and switches. You can see section 2, how to set up the lab, for step-by-step instructions on how to set up and use Packet Tracer for the course lab exercises. After you've passed your CCNA, you're going to be working as a network engineer on real networks with real routers and switches. So of course, you're going to need to know how to connect to those real routers and switches as well, and that's what we're going to cover here. So when you are connecting to real routers and switches, you're going to use some software on your laptop to do that. And the most commonly used software to use is Putty, which is free software. But again, for the lab exercises in this course, you're not using Putty, you're not connecting to a real device, you're using Packet Tracer. So for this course, you do not need to install or use Putty. Okay, so let's carry on and see how this is going to work. So in your day-to-day tasks as a network engineer, you're not actually going to be physically touching the network devices. What's going to be happening is you're going to be sat at your desk working on your PC, and the device, the router or switch that you're working on, is going to be in another location. It's going to be in a locked cabinet, either in the same office that you're in, or the office could be anywhere in the world. And you're going to be connecting to that device over the network. And I'm going to show you how to do that now. So for example, let's say that you, working as a network administrator, you are over here on this PC in London, and you're going to be connecting to this router in New York to work on it. So how are you going to do that? Well, you're going to use software on your PC, which you're going to open, you're then going to connect to the router over the network all the way over in New York. You'll get to the command line and you'll be able to work on that router. So to get to the command line interface for your day-to-day management of Cisco devices, the protocol that you're going to be using in that software is called Secure Shell, SSH, and you're going to connect to the management IP address of the device. There is also another protocol supported, which is Telnet, but it is very not recommended to use that because it is insecure. So with both SSH and Telnet, they look and work exactly the same way. But the difference is that when you're entering commands in SSH, those commands are encrypted. When you enter commands in Telnet, they're unencrypted. So if anybody is sniffing your traffic over the network, they can see those commands, including your username and password. So Telnet is not used in real networks. It can be handy in a lab environment, but in a real corporate environment, you're going to be using SSH. As well as using SSH, also for security, secure login is going to typically be enforced, meaning that you have to enter a valid username and password. So we've got usernames and passwords to log in our devices. Your company's maybe got 100 different devices. You don't want to have to configure all your administrators' usernames and passwords on all 100 of those devices separately. You want that to be centralized. So what you'll have is a centralized AAA server. That stands for Authentication, Authorization, and Accounting. It's got access to the central database of all your usernames and passwords, saves you having them on each separate device. We're going to be covering SSH and AAA, including how to configure them in later lessons. I'm not going to cover it here because we need to have all the other settings on the device set up already as well. We haven't even configured an IP address yet, so I need to go through all of those other basic settings first. I'll show you how to configure SSH and AAA in later lectures in the course. Okay, but I can show you right now how this is going to actually work. So let's have a look at that. The first thing that we need to do is to actually download and install Putty. So to find Putty, it's very easy. We can just go to Google, and I'm going to Google for Putty download.
Yeah, I already have
And then it's this first entry
I
here
call
at
it Putty.
putty.org. I will
Putty.
click on that, and then I can see I can download
I
Putty
call
here.
it Putty
I will click
because it's pretty.
link, and then I'm on a 64-bit Windows machine here, so I am going to download the 64-bit Windows file. So I will click on that,
That's
and it's
the
very
one for
small.
me.
I can see that it has downloaded already.
Although
So
I will
I
not need
will
to use it,
go
so
to
no need for
my
that.
downloads folder. I will double click on the Putty installer here. So I click next on the welcome screen. I'm happy to install it into program files Putty. Click next again. I'll accept all the defaults here and click on install, and then click on finish. So that was in program files and Putty. So I could create a desktop for a shortcut for this on my desktop. I'm just going to run the Putty executable file there, and this is what Putty looks like. And you can see in here that I've got my different connection types. So for connecting to a Cisco device, you can use Telnet or SSH or Serial, that I'll cover in the next lecture. We don't want to use Telnet because it's insecure. We're going to be using SSH, and I need to enter the IP address or host name of the device I'm connecting to. So my router is at 192.168.1.254. I'll enter that IP address, and then I will click on open. And because SSH is a secure protocol, it's giving me this warning message here about the exchange algorithm. I just click yes to say that I do want to continue. And then I get another warning message. I click yes on that as well. And I can see that it says up here, who do I want to log in as? Now, I know this is going to look very small for you, so let me also show you how you can customize the Putty settings. So I'll click on
I'll
the
probably
Putty
be using
icon
like
up here in the
Linux or
top left.
something.
I right click on there,
I prefer
and
using
then I'm
Linux
going to
to
go
SSH
change
into things.
settings. And you can see you can change things like the colors, the appearance, and so on in here. I'm going to go to appearance, and for the font, I'm going to change that, and I'm going to bring it all the way up to 22 just to make it easier for you to see, and then click on apply. So I'm going to log in as the user I already created on this real router, which was Neil. And then I've also configured a warning message that it's only for authorized users. And then I'll also enter in my password there as well. And you can see I am now connected onto the New York router. So very simple to connect to real Cisco devices
Very
over the network.
simple.
Just download PuTTY, then open PuTTY, enter the IP address of the device that you want to connect to, enter in your username and password. If that has
Yep.
been configured in your corporate network, which it most likely will be, you're now on the command line of the router and you can start configuring it. Okay, one last thing that I want to talk about here, and that is out-of-band management. So let me go back to the slides again. And you saw in that example there that I was the administrator over on the PC here, connecting over the corporate network onto the router in New York. And that traffic was going over the production network. What the production network means is the network that is being used for your normal user traffic, the network that is used for your staff in their normal activities. So for example, let's say we've got a normal staff member on their laptop here, and they are connecting to an email server, for example, over in New York. Well, when they connect to it, they're connecting over this network path here. That's the production network. And that was the same path that you went over when you were connecting to the router. So you can connect to the router for management over the normal production network. What you'll find most large companies do is they'll also have a separate dedicated network for management as well. So it looks like this. The reason that they put in a separate dedicated management network is maybe there's a problem with the router in New York over the production network, and you're not able to connect to it over there. So by having a separate dedicated management network, that gives you a backup path that you can use to connect to your network devices if they have any problems. It's also more secure having a separate dedicated path as well. So now we've got two paths that we can use to get to our router. When you do have a separate management network set up, if you're connecting over the production network, we call that in-band management. You're going in-band over the production network, going over the same cables that your normal users are using to connect between offices. If you connect over that separate management network, we call that out-of-band management. It's out of band, not over the same path as your normal staff. I will click on PuTTY settings. So I'll click on the PuTTY icon up here in the top left. I right click on there, and then I'm going to go change settings. And you can see you can change things like the colors, the appearance, and so on in here. I'm going to go to appearance.
I'm sorry.
Hello?
If you have a mailbox on
And for the font, I'm going to change that, and I'm going to bring it all the way up to 22 just to make it easier for you to see, and then click on apply. So I'm going to log in as the user I already created on this real router, which was Neil. And then I've also configured a warning message that it's only for authorized users. And then I'll also enter in my password there as well. And you can see I am now connected onto the New York router. So very simple to connect to real Cisco devices over the network. Just download PuTTY, then open PuTTY, enter the IP address of the device that you want to connect to, enter in your username and password. If that has been configured in your corporate network, which it most likely will be, you're now on the command line of the router and you can start configuring it. Okay, one last thing that I want to talk about here, and that is out-of-band management. So let me go back to the slides again. And you saw in that example there that I was the administrator over on the PC here, connecting over the corporate network onto the router in New York. and that traffic was going over the production network. What the production network means is the network that is being used for your normal user traffic, the network that is used for your staff in their normal activities. So, for example, let's say we've got a normal staff member on their laptop here, and they are connecting to an email server, for example, over in New York. Well, when they connect to it, they're connecting over this network path here. That's the production network. And that was the same path that you went over when you were connecting to the router. So you can connect to the router for management over the normal production network. What you'll find most large companies do is they'll also have a separate dedicated network for management as well. So it looks like this. The reason that they put in a separate dedicated management network is maybe there's a problem with the router in New York over the production network, and you're not able to connect to it over there. So by having a separate dedicated management network, that gives you a backup path that you can use to connect to your network devices if they have any problems. It's also more secure having a separate dedicated path as well. So now we've got two paths that we can use to get to our router. When you do have a separate management network set up, if you're connecting over the production network, we call that in-band management. You're going in band over the production network, going over the same cables that your normal users are using to connect between offices. If you connect over that separate management network, we call that out of band management. It's out of band, not over the same path as your normal staff traffic. If you connect over that separate management network, we call that out of band management. It's out of band, not over the same path as your normal staff traffic. Okay, so that was everything I needed to show you here about connecting over the network. In the next lecture, I'll show you how you can connect to a router over a direct console connection. In the last lecture, I showed you how to connect to a Cisco router or switch over the network. In this lecture, I'll show you how to make a direct connection using a console cable. Before we start, I'll give you a quick reminder that the lab exercises in this course use Cisco Packt simulation software, and you can see how to install and use that by watching section 2, how to set up the lab. So for the lab exercises we're going to be using in the course, you don't need any physical devices and you don't need to install or use PuTTY. But when you go and you start working on real devices in the real world, you are going to need to know how to do this, how to make the initial connection to a physical device. So that's why I'm going to show you here. Cisco devices do not usually have a default IP address, so we need to set one up before we can connect to it over the network. As you saw in the last lecture, I used PuTTY to connect to the management IP address of the device. But what if the device does not have an IP address on it yet? Well, we need a way to connect to the device to do the initial configuration when we first buy it, including adding IP addresses. And that is where the console connection comes in. So with the console connection, we can directly connect to the device at a lower level below IP, get onto the command line there, then we can get to do the initial configuration, including adding the IP address, and once we've done that, we'll then be able to connect to it over the network. So for that initial direct connection, you connect to the console port on the router or switch. I'll show you that in a second. And you use a console cable to do it, which comes in the box with your device.
Hello. Uh, I just made it crazy, crazy, crazy. My gosh. How will this work? I will make it work somehow. I will. You know, the problem is that it's gonna be a help desk. It's like it's gonna be a. I would really prefer if I had like a laid back one. Hmm. Hmm. Gotta think about that. You know, what if I don't want any of the job benefits, but I want my, salary to be increased instead? I'm gonna try that.
And the
Anyways,
console
gotta
cable
be
looks
focused.
like this. You can see that it has got a serial DB9 connector on one end. It's called DB9 because 9 pins go in here. And on the other side, it's got an RJ45 connector, similar to what you would see on a standard Ethernet cable. But this is absolutely not an Ethernet cable. It's not using Ethernet and it doesn't require IP addresses. This gives you a low level direct access to the command line. Now, when you connect this into your router or switch, it's the RJ45 end that plugs into the console port on the device, and it is the serial connector that plugs into your laptop. And this gives us a problem because laptops don't come with serial ports anymore. About 20 years ago, they did, and serial ports were most commonly used to connect to old style 56K modems. They don't exist anymore, so manufacturers don't put the ports on our laptops anymore. So, how are we going to be able to plug this cable into our laptop? Well, what we need to do is buy an additional USB to serial adapter. So you can see here it has got a USB connector on one end and it's got a male serial DB9 connector on the other. So we end up having the USB connector plugged into our laptop or our PC. That then has the cable going into the console cable with the serial connectors here, and then we've got the RJ45 connector that plugs into the router or switch. Oh, okay, so Cisco realized that that's a problem because devices don't have those old style connectors anymore. So with newer devices, it comes with a newer cable, which has got USB on one side to plug into your laptop and mini USB on the other side to plug into the device. Okay, so let's see how this looks on a router now. So I've got in front of me here an old 2600 router from Cisco. This used to be a
Oh,
very
that's nice.
popular workhorse router. And you can see on the back here where I've got my finger now, that is the aux or auxiliary port. And that used to be used for out-of-band management with those old 56K modems.
Mhm.
Again, they don't exist anymore, so that doesn't really get used anymore, this port. Next to it, we have got the blue console port. That is where I've got my console cable plugged in. Then I've got a couple of onboard Ethernet ports on this particular router and a couple of slots up at the top here where we can put in optional cards. And I happen to have an ADSL card fitted in here. Okay, so I have got my router there with the console port plugged into it. And you can see at the other end of my console cable, I have got my USB to serial adapter here, and I'm going to plug this end into my PC. Okay, so I've done that, and I've also plugged in the power lead in the router as well, so we're ready to make the initial connection to the device. The software that I'm going to use for that is Putty again, the same as what I used to make a connection over the network. I showed you in the last video how to download and install that. Just as a quick reminder, again, you can go to Google and just search for Putty download. And then the first link here, that is where you download and can install it from. Okay, so I've already got Putty installed on here. So I'm going to open up Putty, and the type of connection we need to use here to connect to the console port is serial. So I will click on that, and you can see it's showing in here the serial line
Okay, so while
and the speed.
while he
You
is
need to
connecting
select
through
your
that, I will
COM
try to
port
launch
on
my
your
packet
computer
tracer.
here. So the way you find out that information is open up Device Manager in Windows, and then look in your ports here, and you'll see the COM port, and it's usually COM3. Again, you need to have installed the driver software for the cable before this is going to show up. Okay, so I need to change this to COM3. Next thing is we've got the speed, and there's actually more settings in
Man,
this.
that
If you
quality is
go
really
to
bad.
serial over in the main window in Putty here on the
I
left,
can't see that well.
and there you can see again I'm using COM3 for this connection, and I need to have the correct settings here. The default settings are actually
So he has that. For me,
so
I'll
the
probably
speed
have
is
to look over for
9600. I've got 8 data bits, 1 stop bits. The parity is
I don't know. I
none,
remember
and I
being able
should
to
set the
change
flow
this.
control to none as well. But if you leave the flow control as the default, it will still connect anyway. Okay, so now I can go back to session up at the top here, and I can click on open. And I'm not going to see anything yet because I haven't powered my router on. So I'll just reach over here to the power switch on the back of the
All
router,
right.
and I'm flicking it on now, and you can see now I start getting output from the router. So you can see that when you connect over the console connection, as soon as you power the device on, you're immediately connected to the command line, and you can view the device booting up. This is going to take a few minutes to boot up here, so I'm going to speed up the video so we can watch it go through the boot up process. Okay, and that is the router fully booted up. And I see the message here, would you like to enter the initial configuration dialog? That's because I already factory reset this router. It's in the same state as if you bought a brand new router straight from the factory. So that's how you would connect to a new device and get to this prompt here and then start setting it up, putting on the IP addresses, etc. Now, hopefully it's obvious that it's not just for setting up new devices that you can use the console cable, and the device does not need to be powered off when you first connect to it. You could have a device that's already fully configured and powered on, and in your cabinet, you can connect to it with a console cable, and you will immediately get to the live command prompt. Okay, so that's everything I needed to show you about how to use the console connection. Okay, so you saw there that when we get a new device from the factory, we can connect to it with a console cable to do the initial configuration, including adding IP addresses, and we'll then be able to connect.
I guess the con of using the console port is that you will need to be there in person in order to use it. That's a big con. Oh. Mm.
It over the network later. But the console port is not just useful for the initial configuration of a device. You'll often see that it comes in useful for troubleshooting as well. So for example, let's say that we are trying to connect to an existing device on its IP address, but we cannot connect to it. Well, often one of the first things you'll do in that situation is you will plug into it with a console cable to see what is going on, because you don't need the IP address to be responsive to connect it over the console cable. Another thing is if a device just appears to be completely unresponsive, but you can see that it is powering on. So that indicates that the device is probably failing to boot up. Well, again, trying to connect it over the network is not going to work, because the IP address on the device is not live until it has completed the boot up process. So if it's not able to boot up, it doesn't have an IP address on there, you're not going to be able to connect it over the network. But what you can do is you can connect it with the console cable, then power the device on, and when you do it that way, you can watch the device booting up. So if it is having a problem completing the boot up, you'll be able to see what's going wrong over the console connection. Okay, that was everything I needed to tell you here. See you in the next lecture.
Okay.
In this lecture, you're going to learn about how to navigate.
Well, the audio is much worse than this one.
iOS command line.
And I didn't even adjust the music. Oh no, this is gonna be copyrighted. Shit. What's this next? Okay.
Now, the way it's going to be done is through a live demo in the lab. And because I've got a heap of tips and tricks to show you for how to make your way around the command line, to to save you taking your own notes as we go through here, I'm also going to attach a PDF, which is a summary of everything that we're going to cover here. The scenario you see here is I've got a brand new router, I've taken it
No,
out
no,
of
I
the
can't.
box, and I've hooked up a console
I can't see the
cable,
PDFs.
and then I've powered the router on. It's currently going through the boot up process.
I guess that's the bad
And
part
because
about.
it is a brand new router, it's going to ask me, would you like to enter
Because that's the bad
initial
part about
configuration
this.
dialog? If I
What's
entered
it called?
yes here, it would take me to
Coursera.
the command line
So
that
we
the
don't have
wizard,
these
which will tell me
courses
to
like
the initial setup.
we don't
It's
have these
not commonly
courses
used. Normally you would
PDFs.
enter no here.
So I guess the
Button
only way is to
here.
learn is just to see
Ask me,
him
would I like to
do what
terminate
he's doing.
auto install? Yes, I would like to terminate that. You see my
Okay, so
interface is on the router.
I will just have to set up my own. Let me see packet tracer. Let me see if that's possible. All right. So we just need to duplicate or replicate what he has. I believe he has a. Oof, and I cannot see well with this light hitting me. Okay, so what we need is a switch. Hold on. Router switches. Which switch does he have? Cisco iOS, support technical, switch systems, CS2, C2, C28, 11. Is that the model? Okay, let's see if we can find that. Oh my gosh, the light is too much. How can I? No, that's only there. Even in full screen, I am unable to see that well. I can't see that well. I might have to turn off the lights. Okay. All right, turn off the lights. But I still cannot focus. Okay. The things are so small, man. Simulation. No, real time. Root. Yeah. Physical. Logical. Windows extension, edit options, view. It's in preferences. Everything looks so small, like all of them. Oh, fonts. Okay. My gosh. They wanted to kill me with this, man. Even bigger. All right. That's too much. Cisco networking, image cleanup, show. All right. Dialog, toolkit. Set its size. That's the smallest it could be. Okay, general interface, that's that. Let's make it about 10. hold on. Okay. All right. Now I'm able to see now, so that's way better. That's much better than before. I can turn on background light. Still, that light is still light though. Okay. Okay. Yeah. Okay. That's just fine. I don't mind it being like that. Okay. All right. Okay. We got that. So what I want is that's the 26. I want to see. Anyways, we can have any switch. All right, let's see. Does it have a console login? Yep, it has a console login. Okay. So we can have that, and then we can just get a device, let's say a laptop, since he works without power. Okay. Config. Here's the CLI. Looks like we didn't have to use the console to log in.
Way around the command line. To save you taking your own notes as we go through here, I'm also going to attach a PDF, which is a summary of everything that we're going to cover here. The scenario you see here is I've got a brand new router, I've taken it out of the box, and I've hooked up a console cable, and then I've powered the router on, and it's currently going through the boot up process. And because it is a brand new router, it's going to ask me, would you like to enter the initial configuration dialog? If I entered yes here, it would take me to a command line driven wizard, which would help me do the initial setup.
Oh no, I think I remember this.
Normally we'll enter no here, so that's what I'll do here. Ask me, would I like to terminate auto install? Yes, I would like to terminate that. I'll see my interfaces on the router coming up, and then I land at the user exec prompt. Now, we're not commonly going to be working at the user exec prompt because there's a very limited set of commands that
Config,
we can enter here.
desktop, can go into
I'll enter
command prompt or terminal.
So
Hold on.
question mark on the keyboard
Cisco.
there, and it shows me all of the commands that are available at user exec mode. Notice down at the bottom,
host name and IP,
indicates that there's additional
config,
additional
settings,
that I can see. I can hit the enter key,
interface,
and that will scroll
physical,
through it
that's the
line
physical,
by
that's the
line,
config.
But this would be a fairly tedious way to scroll through a lot of output. So what I'll do instead is I'll hit the space bar, and that's going to scroll through it page by page. So I can just hit the space bar multiple times until I get to the end of the output there. Notice in PuTTY over on the right here, I can scroll back through the previous output. Now, by default in PuTTY, it doesn't include a lot of lines of scroll back. So what I can do to improve that is go up in the top left here, right click, and change settings. And if I then go to the window tab, I can set my lines of scroll back here to 2000. I've done that already. By default, you're going to see a much smaller value here, and that can be annoying because sometimes you do need to scroll back through quite a few lines of output. So I'd recommend that you set this to a high value. Okay, so you saw that I can hit the question mark to see all of the available commands that are available at this level in the command hierarchy. And as I said earlier, there's not really a lot that I can do at the user prompt, so I'm going to go to privileged exec mode. To get there, the command I need to enter is enable. So I hit enable, and notice that the command prompt changes. When I was
Incomplete.
in user exec mode, the prompt showed the name of my router, which is just router, the default right now, and then a greater than symbol. But
Yeah.
when I go to the privileged exec mode with the enable command, it changes to show the host name and then a hash.
A
So
hash.
you can tell by the command prompt what level you're currently at. If I wanted
This is
to
a
drop back
switch.
down to the user,
He's on a router. I am on a switch. Hold on. Okay, looks like the device is booting with us without us having to do anything. Ah, there we go. We find our way to it. We find our way to the router. So now we are able to config. Oh, y'all probably can't see that, can you? Um, so this is the router. So it was powering up and now it's on. I mean, it looks about the same. Yeah, it's the same as the one that he has.
So I'm going to now by dead as I'll hit this R, I'll see my and it's currently going.
It's the same one that he has. Onboard VPN.
On the right here, I hear ask me would I like to terminate auto install? Yes, I would like to terminate that. I'll see my interfaces on the router coming up, and then I land at the user exec prompt. Now, we're not commonly going to be working at the user.
You're going to enable. You just did that.
Limited set of commands that we can enter here. If I want to see what those commands are, I'll enter a question mark. So I just hit question mark on the keyboard there, and it shows me all of the commands that are available at user exec mode. Notice down at the bottom I see more here. This indicates that there's additional commands, additional output that I could see. I can hit the enter key and that will scroll through it line by line, but this would be a fairly tedious way to scroll through a lot of output. So what I'll do instead is I'll hit the space bar, and that's going to scroll through it page by page. So I can just hit the space bar multiple times until I get to the end of the output there. Notice in PuTTY over on the
Configure
right here,
VLAN
I can
parameters.
scroll back through the previous output. Now, by default in PuTTY, it doesn't include a lot of lines of scroll back. So what I can do to improve that is go up in the top left here, right click, and change settings. And if I then go to the window tab, I can set my lines of scroll back here to 2000. I've done that already. By default, you're going to see a much smaller value here, and that can be annoying because sometimes you do need to scroll back through quite a few lines of output. So I'd recommend that you set this to a high value. Okay, so you saw that I can hit the question mark to see all of the available commands that are available at this level in the command hierarchy. And as I said earlier, there's not really a lot that I can do at the user prompt, so I'm going to go to privileged exec mode. To get there, the command I need to enter is enable. So I hit enable, and notice that the
Now,
command
from what I know is
that
enable,
is
and the users,
user
they have
exec
like,
mode. The
different
prompt
commands and
shows
stuff.
the name of my router, which is just router, the default right now, and then a greater than symbol. But when I go to the privileged exec mode with the enable command, it changes to show the host name and then a hash. So you can tell by the command prompt what level you're currently at. If I wanted to drop back down to the user level, which normally you wouldn't want to do, I can enter the disable command.
Disable.
Okay, so now I'm going to go back up to
Enable.
the
Okay.
privileged exec mode, which is also known as the enable prompt, and I'll show you that we can use command abbreviation here. So rather than typing in the full command enable, I can just say EN and hit enter, and that will bring me
Oh, so what about
I could
this?
also use an abbreviated command to go back down to the user prompt again. So I'll try entering DI and hit enter. But what I see now is that this is an ambiguous command. The reason for this is whenever you use command abbreviation, there has to be just one possible unique match. So
Yeah,
if I now
disable.
enter
There's
DI
there's
and
disconnect. There's
question mark, it will show
yeah.
me all of the possible commands that begin with DI. And you can see that there's three possible commands here: dir, disable, and disconnect. So when I typed in DI, it didn't know which one I meant. So if I wanted to actually put in the
Oh no.
abbreviation for disable, I'd have to enter
It's the
DISK,
error, or
and it
like
would now know, okay, there's only
translating
one possible command, I
this.
must mean disable. I don't need to go back down a level though, so I'll just stay at
It's
the
too much.
user
Like
prompt for
it
now.
takes a long
Next up,
time.
I'm going to check what
It
all
takes a long
commands
time to
begin
go to
with
get out.
SH. So I'll enter SH and a question mark, and I can see there's only one possible command, which is show. On Cisco routers and switches, you will use the show command a lot because we use it to get information about the device. So the shortest way we can type that is just SH. If you want to see what the available show commands are, I'm going to put the same command in, but I'm going to have a space now. So it's SH space and then question mark. When you include a space, it shows you all of the possible keywords for that particular command. So this is the context-sensitive help now. So again, I can see all my different show commands here.
That's good. That's good. That's good. So you can do like the also
If I wanted to break out of a command output without
dear.
scrolling all the way to the end, I can hit the
You can do
control button,
dear flash 01.
that will break out of the command.
Oh, so
And
show
if I scroll
zone.
back, you'll notice the first available option there was show AAA. So let's use that for our example and show you how you can figure out commands with the context
Okay,
sensitive.
show
So if I
IP.
type in show AAA space question mark, it shows me all of the available options that would be available after show.
It'll be show dash IP.
If you need to enter
No.
a particular command, but you can't remember exactly what command you needed to enter, this can be really helpful in that situation. Similarly to the command abbreviation, we can also do tab completion as well. For example, you see my first option here is show AAA accounting stop cache. that's quite long to type in. So what I'm going to do instead is I'm going to say show AAA ACC, which makes it a unique match. And now I can hit the tab key and that will auto-complete the entire word for me. While I'm at the command line, I can use the backspace to delete what I'd entered already. So that's what I'm doing here. And let's deliberately put in a typo here. So notice I've put show AAA accounting stock quiche. That should be cache. So I've put in a typo. If I hit enter, you'll see I get the error message, invalid input detected. When you get this error, it's usually because you put a typo in. And I can see the marker here shows me
So
exactly where that
this
typo is.
also,
Let's have a
it
look at
has
the
its
other
own.
error. So if I do
So yeah, you gotta do show
enter,
AAA
you see the error I now
local.
get is incomplete
Not local?
command. I have to carry on with the command by putting
So what?
in one of these
How do I
additional
use it then?
options here.
AAA
Do a show
dash
run
local.
question mark as an example. Carriage return, that means that I could hit enter. These are all optional keywords. I don't have to enter one. I could actually hit an
Okay.
enter here to get some
What
out.
about local?
So at the enable prompt, that's where we'll most commonly be using
Okay,
show
so
commands.
local
The other
user
command we'll use here
brother
are
local
question mark,
root.
and I'll see all of the possible debugs here. The difference between a show command and a debug, when you
Whatever
enter
that
a show
means,
command,
man.
it gives you point in time information about the state right now. When you do a debug, what will happen is that the output will be updated in real time. So for example, if you were debugging OSPF and an OSPF packet came in, you would see it show up as and when the packet came in. Okay, next thing I want to show you is how to actually make configuration changes on the router or switch. At the enable prompt, that's mostly for information there. To actually make changes, we go to global configuration. To get there, it's configure terminal. Now the abbreviation for this is you can just type in conft. You'll use this command a lot, so you'll be using conft a lot as well.
Okay, into configuration command one per line. And with
let's hit the
C
question mark, see
and
all the available commands here. So we could do that the same as we did at the enable prompt. If I hit Control C to break out of this, another thing to notice is that the prompt changed again. So when we were at the enable prompt, the prompt showed our hostname and then a hash. When we're at global configuration, it's router and then config in brackets. So the hostname, config in brackets, and then a hash. Okay, we're up to the 10-minute mark in this lecture. I know when I'm learning, changes.
wait.
At the enable prompt, that's mostly for information there. To actually do that the same as we did at the enable prompt, if I hit Control C to break out of this, another thing to notice is that the prompt changed again. So when we were
Okay,
at the
router
config,
Control C,
the prompt showed
configuration from
and then a hash,
and then router,
global
and then we
it's
do
router and then config
disable.
in brackets. So the host name, config in brackets, and then a hash. Okay, we're up to
Or is
the
disabled by,
mark.
or is it by like one?
I know when I'm learning, I don't like to sit too long. I like to take frequent breaks. So what I'm going to do for this lecture is I'm going to split it into two parts, which are going to be about 10 minutes each. So go get yourself a coffee, and I'll see you back here for.
I don't drink coffee. Okay, part 2. There are no flashcards.
Command history works in a second, so I'm just going to enter a couple.
Okay.
of
Continue.
random commands in here. It's just adding a couple of host entries. Don't worry too much about what this command does. It's not important. I'm just using this to illustrate the command history coming up in a second. So I'm adding IP host server 1 and IP host server 2. Next, I'm going to change the name of my router. I'm going to give it a host name, but I'm going to deliberately make a mistake here.
Wait.
What this command does, it's not important. I'm just using this to illustrate the command history coming up in a second. So I'm adding IP host server 1 and IP host server 2. Next, I'm going to change the name of my router. I'm going to give it a host name, but I'm going to deliberately make a mistake here.
Hold on.
So I type in
Okay, so I have to be,
and hit enter.
first I have to enable. All right, and then after enabling, I have to do configure terminal, all right? And then in config, then I'll be IP host server 1.1.1.1. Okay, then I'm gonna do the same thing, but for server 2.2.2.2.2. Okay.
Enter, and you'll see it tells me invalid input detected at the marker. It's because I forgot to say host name at the start here. So let's correct that, but rather than typing the whole thing in again, when you make a typo on a command, the quickest way to correct it is to hit the up arrow, and then that will bring the previous command back again. Now what I could do is I can use the left arrow to move the cursor to the left. But if it's a big long command, a way that you can do this quicker is by hitting Control A, and that will bring you to the start of the line. So I hit the up arrow, the previous command.
Control A. Wow, what about Control S? Control D? That's just deletes. Control F, it moves you. Control W deletes. Control Q, Control E. Okay, Control A at the start. Control E to the end. Okay. All right. Let me write that tip down right here. Okay.
Then Control A to move to the start of the line, and I can now type in host name and a space, and that's the correct command now. So I hit enter, and notice that the prompt changes to reflect the host
Router
name that I
one.
just entered there. Next, I'm going to show you command history. So I'm going to hit the up arrow a few times, and you'll see each time I hit the up arrow, it cycles back through my previous commands. That's why I entered those commands earlier. Notice that it only cycles back through commands at the same level. I'm in global configuration here, so it's cycling back through the commands I entered in global configuration mode. It doesn't show the commands that I entered at the enable prompt or in the user mode. Now I'm just going to delete this command to show you the next thing. While I'm in global configuration, if I try to do a show command, so let's do a show IP interface brief, and I hit enter and I get the invalid input detected. You know I said earlier that where you'll most often see this is if you've put in a typo. The other place where you'll often see it is if you're at the wrong command level. When you're a beginner, this is the most frustrating thing about the iOS command line. You'll make this mistake a lot where you're going to be at the wrong level when you enter a command. Our show and our debug commands are entered in privileged exec mode at the enable prompt. If I try to put it in global config, it's going to give me an error message. But this could be really annoying. So thankfully there's a workaround for this when you want to enter a show command, because it is very common to put show commands in. And what I can do is I'm going to enter the same command, but I'm going to put do at the front. So again, I'm going to use the command history here. Rather than typing the whole thing in, I hit the up arrow to get the command back, then Control A to go back to the start of the line. Then I type in do and a space and hit enter, and you'll see that the show command is going to work now. And when you enter do, that will work from any level unless you're actually in privileged exec mode. At privileged exec mode, you have to do the show command without do. At all the other levels, you put do in front of the show.
Okay.
The command back, then Control A to go back to the start of the line. Then I type in do and a space and hit enter, and you'll see that the show command is going to work now. And when you enter do, that will work from any.
Probably navigating iOS. Probably have the tips here. Okay.
Level, and
okay, when trying to use the show command, make sure to type it in as no, I don't need as
in privileged exec mode. At privileged exec mode, you have to do the show command without do. At all the other levels, you put
privilege use, right?
Unless you're actually in privileged exec mode. At privileged exec mode, you have to do the show command without do. At all the other levels, you put do in front of the show, and then it's going to work. So far we've seen the user
kind of like in Linux with the root. You gotta be in root in order to do root levels.
There's other levels when you're configuring something specific on the router.
So can I really into exec?
I would do my
no
configuration for things that affect the router as a whole. If I
okay,
I
interface, unassigned.
need to go to that level in the command hierarchy. So looking at my output here, I can see the interfaces I've got available on this router. If I wanted to configure interface fast Ethernet 00, for example, putting an IP address on there, I have to go to interface configuration mode. So to get there, the command is interface, and I'll use tab complete.
Okay.
I would do my global configuration for things that affect the router as a whole. If I wanted to configure a specific interface, I need to go to that level in the command hierarchy. So looking at my output here, I can see the interfaces I've got available on this router. If I wanted to configure interface fast Ethernet 00, for example, putting an IP address on there, I have to go to interface configuration mode. So to get there, the command is interface, and I'll use tab completion here. So interface fast Ethernet 0/0. And notice here that in the output above, Fast Ethernet, that was capitalized at the start. Here, I don't need to use capital letters. iOS is not case sensitive. It doesn't matter if you use uppercase or lowercase, with one exception that we'll talk about a little bit later in this lecture. So I go to interface Fast Ethernet 00, hit enter. You'll see that the command.
Okay, let's see. In our case, it's Fast Ethernet 00. Okay, so interface Fast Ethernet 0-2. Okay, there we are.
And prompt changes again to show config-f, and I can see very clearly that I'm at the interface configuration level. If I want to drop back down a level, I enter the exit command, and that takes me
To go down a level. Okay. Okay, probably need to do use the enable /in to enable global what's it called, to enable global configuration. To enable global configuration. And disable to, no need to just list it out for you. That's that. Use enable. Use exit to go down a level, like from exec to normal. Level.
me back to global config.
I really hate this big old bar right here, especially like when you pause and then it's just there. I hate it so much. I wish that I could remove it, but cause most of the things that we're working with are down here, and then when I pause, it's like I can't see them. This is much better, but I don't know if it will show up.
If I wanted to go to the enable prompt again, I would enter exit again, and that will drop me back to the enable prompt. To privileged exec mode. Notice from here, I can enter interface Fast Ethernet 0/0. This is going to give me an error message because you have to go up through the levels one by one.
For
you can't skip straight from the enable
some
prompt
commands,
to the
you
interface
will
prompt.
need to
So I'll
go
back through
up
the
levels
so I enter config
in
to
order
get to
to
global
use
configuration,
them.
and then interface Fast 0/0 to get to the interface mode. So when you go up through the levels, you have to go one by one. When you drop back down the levels, you can actually do that all in one go. So it was exit to drop down one level. To drop all the way back to the enable prompt with one command, I can enter end. Another way I could have done that.
Okay. You can use and to go down all levels till the start. Exa example router.
That would be by hitting Control C on the keyboard. Okay, a Cisco router or switch is the show IP interface brief that you saw earlier. That will show all the interfaces on the router and the state of the interface, whether it's up or not, and also the IP address configured on the interface as well, if there's an IP address on there. The other show command that is used really, really often is show running config. That shows the entire configuration on the router.
Show.
And I'll hit the spacebar here to scroll through the used really, really often is show running config. That
Show
shows the
running
entire configuration
config.
on the router. And I'll hit the spacebar here to scroll through the configuration, and you can see even on a new router, it's a really long configuration file, and it's going to take quite a while to scroll through there. On a production router, it's
Hold on. So I can use it here. So let's use exit. Show running config. So can use it here. Let's exit. Okay, so all right. Until the, I guess can't do that. Can also do page down. Oops. IP host server 1. Okay. Aux login. And that's the end. Okay.
going to be even longer because there's going to be actual configuration in there. There are switches we can use for the show run command which are going to help us target the actual part of the configuration that we want to look at. For example, if I want to look at the configuration for a particular interface, I can do show run interface and then the interface I'm interested in, and it shows me just that part of the configuration. So to see the interface config, it's show run and then interface and the interface number. The other switches that we can use on the show run command use a pipe. And to give you an example of that, I can do a show run and then the pipe symbol, which looks like that. And then the available options after there, the ones that are most commonly used, begin is probably the most commonly used. I can also include and exclude as well. So for example, I could do show run begin hostname, and this will show me the running config, but starting from where hostname shows up in the running configuration. Now, you know I said that there's an exception to when the iOS command line is case sensitive or not. Well, when you use a pipe, this is actually using a regular expression which is case sensitive. So if I did a show run pipe begin, and try not to put a typo in, and then hostname with a capital H and hit enter, you'll see it's going to just go straight back to the command line again. This is not an error. The reason is that hostname with a capital H is not in the running config at all, so there's no output to show. To give you examples for the other pipe options, I could do a show run and then pipe it to include interface, and it'll show me all the lines that include interface, meaning the word interface in the actual output. I can also do a show run and pipe that and exclude interface. This will show me all lines from the configuration that do not include the word interface. And I can also do a show run and pipe and section interface. That will show me the configuration for all my different interfaces. Now, when you've got a production router, you're not going to just have interfaces configured on there. You'll have other things like routing protocols, for example. So I could also do a show run pipe it section and put in the particular part of the configuration I want to see here. Now, if you put in a question mark, it's not very useful here because it just tells you line telling you to use a regular expression. But for example, I could put in section BGP to see information about the BGP routing protocol. I haven't configured it on this router yet, so I'm not going to get any output, but if I was using BGP on this router and I had a big long configuration on there, this would be a useful command because it would just take me straight to the BGP config and I could see that very clearly. Okay, so that's how to navigate the iOS command line. In the next lecture, we'll take a look at how to manage our configuration files. In this lecture, you're going to learn about iOS configuration management and the running configuration and the startup configuration. So I'm going to make some configuration commands to demonstrate this for you. I'm going to go to global configuration, so I enter config T. Notice right now that I've just got the default set up in this example where the hostname is router. If I enter the command hostname router1 and hit enter, you'll see that the host name changes immediately. So in iOS, whenever you make a change, the change takes effect immediately. When you make the change, it goes into the running configuration, which is the configuration that is in effect right now. But as well as having the running configuration, we've also got the startup configuration. So running config is the config in effect right now. The startup configuration is the configuration that will go into effect when the router is next started or rebooted. And commands that you entered in the running config do not get saved permanently until you explicitly copy them from the running configuration to the startup configuration. So you can see here, I entered the command hostname router1. That went into the running configuration immediately, and my hostname was immediately changed to router1. But if I now do a show startup config, and notice my not so deliberate mistake. I'm at global configuration, so I can't enter a show command. I told you you'd make that mistake a lot, right? I still make that mistake too. So I'll hit Control A and make that a do show start. And let's do tab completion to check what the command should be. So the full command is show startup config. I'll hit enter, and notice here that the host name is still router. It hasn't changed to router1. So in the startup config, it's still hostname router. If I now do a do show running config, In this lecture, you're going to learn about iOS configuration management and the running configuration and the startup configuration. So I'm going to make some configuration commands to demonstrate this for you. I'm going to go to global configuration, so I enter config T. Notice right now that I've just got the default setup in this example where the hostname is router. If I enter the command hostname router1 and hit enter, you'll see that the hostname changes immediately. So in iOS, whenever you make a change, the change takes effect immediately. When you make the change, it goes into the running configuration, which is the configuration that is in effect right now. But as well as having the running configuration, we've also got the startup configuration. So running config is the config in effect right now. The startup configuration is the configuration that will go into effect when the router is next started or rebooted. And commands that you entered in the running config do not get saved permanently until you explicitly copy them from the running configuration to the startup configuration. Which is the configuration that is in effect right now. But as well as having the running configuration, we've also got the startup configuration. So running config is the config in effect right now. The startup configuration is the configuration that will go into effect when the router is next started or rebooted. And commands that you entered in the running config do not get saved permanently until you explicitly copy them from the running configuration to the startup configuration. So you can see here I entered the command hostname router1. That went into the running configuration immediately, and my hostname was immediately changed to router1. But if I now do a show startup config, and notice my not so deliberate mistake. I'm at global configuration, so I can't enter a show command. I told you you'd make that mistake a lot, right? I still make that mistake too. So I'll hit Control A and make that a do show start. And let's do tab completion to check what the command should be. So the full command is show startup config. I'll hit enter, and notice here that the host name is still router. It hasn't changed to router1. So in the startup config, it's still hostname router. If I now do a do show running config, I can see in the running config that the host name is router1. So if I now reloaded the router, it would come back and the change would not have taken effect. Now, this is actually deliberate because it allows you to back the route. I notice configuration, so I can't enter a show to effect when the router is next started or rebooted. And commands that you entered in the running config do not get saved permanently until you explicitly copy them from the running configuration to the startup configuration. So you can see here I entered the command hostname router1. That went into the running configuration immediately, and my hostname was immediately changed to router1. But if I now do a show startup config, Oh, and notice my not so deliberate mistake. I'm at global configuration, so I can't enter a show command. I told you you'd make that mistake a lot, right? I still make that mistake too. So I'll hit Control A and make that a do show start. And let's do tab completion to check what the command should be. So the full command is show startup config. I'll hit enter, and notice here that the host name is still router. It hasn't changed to router 1. So in the startup config, it's still hostname router. If I now do a do show running config, I can see in the running config that the host So in the startup config, it's still hostname router. If I now do a do show running config, I can see in the running config that the hostname is router 1. So if I now reloaded the router, it would come back and the change would not have taken effect. Now, this is actually deliberate because it allows you to back out of mistakes. Say if I made some changes on the router and I made some catastrophic changes, but I hadn't saved it yet, the easiest thing to do is to just pull the power out of the router and then plug it back in again, boot it up, and it will come back with the configuration that was already on there before I'd made those changes. Now, obviously, that's a fairly drastic thing to do. It requires a reboot of the router, so you would only do that as really a last resort. Okay, so I've changed the name of my router to router 1 in my running config. I haven't copied it to the startup config yet though, so it's not going to be persistent across a reboot. To do that, the command is copy run start. And again, I'm at the wrong command level, so I'll end to drop back down to the enable prompt. To do your copy run start command, you have to be at the privileged exec mode. So I can now do a copy run start. It'll ask me the destination file name I want to save it to. Pretty much always we're going to accept the default here and just hit enter. It will take a few seconds to build the configuration, and I get the OK message telling me that yes, it's been copied to the startup config. So if I now do my show startup config command again, you'll see that the host name is now router 1 in there as well, so it's permanent. If I reboot the router now, it's going to come up with that as the configuration. The next thing I want to show you is how to back back up your configuration. Now, Cisco do have tools like Cisco Prime Infrastructure that can be used to automate this from a centralized server. That's not tested on the exam, by the way, but you can also back up manually as well. The way to do that is I'm going to copy the running configuration. I'll hit the question mark now to see where I can copy it to, and you'll see one of the options here is flash, which is flash memory on the router. So I can do a copy running config to flash, and I have to give it a file name when I do this. So I enter a colon and I'll call it my-config. Try to do it without a typo. There we go. It'll say what do I want the destination file name to be. Yes, I want it to be called my-config, and I've now backed up tools like Cisco as the configuration. The next thing I want to show you is how to back up your configuration. Now, Cisco do have tools like Cisco Prime Infrastructure that can be used to automate this from a centralized server. That's not tested on the exam, by the way, but you can also back up manually as well. The way to do that is I'm going to copy the running configuration. I'll hit the question mark now to see where I can copy it to, and you'll see one of the options here is flash, which is flash memory on the router. So I can do a copy running config to flash, and I have to give it a file name when I do this. So I enter a colon and I'll call it my-config. Try to do it without a typo. There we go. It'll say what do I want the destination file name to be. Yes, I want it to be called my-config, and I've now backed up my configuration to flash. To verify that, I can try a show flash, and there you see I've got my-config is in there. If I wanted to restore from this backup, the way I do it is by copying it to the startup config and then rebooting. But when you do a copy, it's going to actually merge the commands rather than replace. And typically I would want to replace the entire startup configuration. So the way I do that is, first off, I erase the startup configuration. So I enter the command erase start. Let's copy. It's going to actually try that. I can try a show flash, and there you see I've got my-config is in there. If I wanted to restore from this backup, the way I do it is by, and there you see I've got my-config is in there. If I wanted to restore from this backup, the way I do it is by copying it to the startup config and then rebooting. But when you do a copy, it's going to actually merge the commands rather than replace. And typically I would want to replace the entire startup configuration. So the way I do that is, first off, I erase the startup configuration. So I enter the command erase start. It's telling me an incomplete command, so let's use the context sensitive help. To help here, I'll hit the up arrow, space question mark, and it tells me unrecognized command. Okay, this is because I'm working on an older router here. So on an older router, the command is write erase, and that will tell me it's going to erase the NVRAM file system, which is where the startup config is saved. Do I want to confirm? I hit enter to confirm that, and that will erase my startup config. I can now copy flash colon my-config to the startup, and that will tell me it's going to erase the NVRAM file system, which is where the startup config is saved. Do I want to confirm? I hit enter to confirm that, and that will erase my startup config. I can now copy flash colon my-config -config to the startup configuration, confirm that, and I would now reboot the router to come back up with that configuration. Now, hopefully you're thinking it's not a very good idea to back up the configuration to flash on this router, because if the entire router blows up, I lose the router and I lose my backup as well. It's always a bad idea to back up a device to the same device. You want to back it up somewhere else. So the easiest way to do that would be to copy the running config to a TFTP server. So I enter copy run TFTP and hit enter. It will then ask me for the IP address of my TFTP server. Let's say this is at 10.10.10.10. I hit enter, then the name of the file name I want to use. Let's say I'm going to use router1-config, and then I could enter today's date in here. Say that that's a date and hit enter. And it will then connect to the TFTP server and back up the configuration there as a text file. I'm getting an error message because I don't actually have a TFTP server in the lab here. While I'm saying that it will show up as a text file, another thing you might wonder is, okay, how do I check what the actual contents of my backup are? If it's saved to flash, the way you can do that is using the more command. So I would enter the command more, and then a space, and then flash : my TFTP server. Let's say this is at 10.10.10.10. I hit enter, then the name of the file name I want to use. Let's say I'm going to use router1-config, and then I could enter today's date in here. Say that that's a date and hit enter. And it will then connect to the TFTP server and back up the configuration there as a text file. I'm getting an error message because I don't actually have a TFTP server in the lab here. While I'm saying that it will show up as a text file, another thing you might wonder is, okay, how do I check what the actual contents of my backup are? If it's saved to flash, the way you can do that is using the more command. So I would enter the command more, and then a space, and then flash : my-config, and that will print out here what the contents of that configuration file are. The last thing that I need to tell you here is where the different configuration files are stored. Now, for the device to boot up, it needs to initially load the iOS operating system image, and that is stored in Flash. Once the operating system is up and running, then it will load your actual administrator configuration from the startup config, and the startup config is stored in NVRAM. That's non-volatile memory, so it's persistent across a reboot. The running configuration is stored in normal memory in RAM, and it's loaded into RAM memory from the startup config when the device boots up. Okay, that's it. See you in the next lecture. We covered an overview of the OSI reference model in a previous section, and you learned about the upper layers then. In this section, we're going to start taking a much deeper look at the bottom 4 layers, which are particularly important for computer networking. We'll start off with layer 4, the transport layer. You'll learn about port numbers, about how TCP and UDP work, and we'll do a comparison between those two protocols. You'll learn about layer 4 of the OSI model, the transport layer, in this lecture. So layer 4, transport layer, it provides transparent transfer of data between hosts and is responsible for end-to-end error recovery and flow control. But as you'll learn as we go through the lecture, that is not mandatory. So maybe the layer 4 protocol will support error recovery and flow control, maybe it won't. You'll see the implications of that as we go through. So, in flow control, it's the process of adjusting the flow of data from the sender to ensure that the receiving host can handle all of it. So if the sender is sending too quickly, maybe because we've got faster network connections on that side, and it's sending more than the receiving host can accept, then if flow control is enabled, the receiving host will have a mechanism to signal back to the sender telling it to slow down. Another thing that is supported at layer 4 is session multiplexing. This is a process by which a host is able to support multiple sessions simultaneously and manage the individual traffic streams over a single. Link. So let's take a look at how that works. So the example here, I've got a sender on the left and there's going to be a couple of receivers over on the right. The sender sends some email SMTP traffic to the top receiver on port 25, and it also sends some web traffic on HTTP port 80 to the bottom receiver, and it's also sending email traffic on port 25 to the bottom receiver as well. So you can see from the sender on the left, we've got 3 sessions from it. The top receiver on the right, we've got 1 session, and on the bottom receiver, we've got 2 sessions. It's layer 4, the transport layer, that is responsible for tracking and keeping control of the different sessions on a host. We have port numbers. So going back to that previous example again, you see we've got 2 sessions going from the sender on the left to the bottom receiver on the right. One of them is web traffic, the other session is email traffic. So when the traffic comes into the receiver, how does it know which application this traffic is for? Is it for its web server application or is it for its email server application? The way it knows is with the layer 4 port numbers. For example, HTTP web traffic uses port 80, SMTP email uses port 25. We'll talk about some of the other common port numbers at the end of the lecture as well. The sender also adds a source port number to the layer 4 header as well. The combination of source and destination port number can be used to track sessions. So let's see how that works as well. So here we've just got one sender on the left, the receiver on the right, and we're sending web traffic again here. So the sender, it sends it with a destination port of port 80, the standard port for web traffic, and it will use a random source port number above 1024. In our example, it's using source port 1500. So we've got a connection between the sender and the receiver. When the receiver sends traffic back, it will flip the source and destination port numbers around. So it will use port 80 as its source now, and the destination will be port number 1500. This is how stateful firewalls are able to keep track of connections as well. Imagine that rather than a switch in the middle there, if it was a firewall, and we had a rule in the firewall that said traffic is allowed out from the sender on the left, out to the network on the right, but traffic is not allowed from the right to the left unless it was initiated from the sender, if you manage to follow that. Well, in that case, on the firewall, we're allowing traffic from the sender to the receiver. That traffic is allowed outbound. When the return traffic comes back, the firewall could see, based on the source and destination port numbers, oh, this is return traffic going back to that sender again, so I'll allow this traffic to come through. If the traffic had been initiated by the host on the right, it would not allow that traffic. Okay, so that's how stateful firewalls work. Our two most common protocols at layer 4 are TCP, which is the Transmission Control Protocol, and UDP, which is the User Datagram Protocol. TCP is connection oriented. As we go through the rest of this lecture, you'll see that a lot of the main characteristics of TCP and UDP are opposite each other. And after I've explained both protocols, I'll explain why that is. So TCP, it's connection oriented, meaning that once a connection is established, data can be sent bidirectionally over the two hosts over that connection. TCP carries out sequencing, so it includes sequence numbers in the traffic to ensure that segments are processed in the correct order and none are missing. So when traffic comes into the receiver, it can look at the sequence number and it can use that to make sure that it assembles the traffic in the correct order again. It can also check from the sequence numbers if a segment was lost in transit as well. TCP is reliable. The receiving host sends acknowledgements back to the sender. So based on the sequence numbers, the receiver can see if all the traffic has come in. If any traffic is being lost in transit, then it will tell the sender that that happened. The way it does it is by not sending an acknowledgement back to the sender. When a sender realizes that traffic has been lost, it will resend that traffic again. TCP can also perform flow control as well. So if the sender is sending at a rate too high and the receiver can't handle it, the receiver can signal back to the sender telling it to slow down. So TCP, it's a connection-oriented, reliable protocol. The way that that connection is set up between the two hosts is it uses the TCP three-way handshake. So here we've got the sender on the left is going to initiate the connection. It sends a SYN, a synchronized message, over to the receiver on the right. When the receiver receives that, it will send a SYN ACK back, so a synchronized acknowledgement, and then finally, to complete the connection, the sender will send an acknowledgement. We now have the connection set up between the two hosts, and we can send traffic over it. The next thing I'm going to show you is the makeup of the TCP header. But just before I show you, I wanted to give you a quick reminder from the previous lesson about how a packet is composed. So here we've got the sender on the left, the receiver on the right, and we're going to send some traffic over there. So first off, as the sender is composing the packet, it will put in the layer 7 information. It will then encapsulate that with the layer 6 header. It then gets encapsulated with the layer 5 header, then layer 4 header, then layer 3 header, layer 2 header, and then we send it onto the physical wire. So what you're going to see in the next slide is how that layer 4 header is composed, what comprises it. And here's how it looks. So we've got the source port and the destination port numbers, as we spoke about just there earlier. We then have the sequence number and the acknowledgement number. We have a header length, a reserved field, which is for any reserved information later, code bits, window, which can be used for flow control, a checksum, which can be used to check and see if the traffic got corrupted in transit. We've got an optional urgent part of the header there as well. We can add other options, and then we've got the data. So you see there's quite a lot that goes into the TCP header. We'll contrast that with the UDP header coming up in a minute. So let's talk about UDP now. UDP is the user datagram protocol, and it sends traffic best effort, meaning we don't have the connection, we don't have reliability. The sender just makes up the packet, sends it over to the receiver, and hopes that it's going to get there. So at UDP, it's not connection oriented. There's no handshake connection set up between the hosts. It doesn't carry out sequencing to ensure segments are processed in the correct order or missing. It's not reliable. The receiving host does not send acknowledgements back to the sender, does not perform flow control. So you know how I just said that the sender will send the traffic and hope it gets there? We can still have error detection and recovery for this traffic, but if it is required, it's going to be up to the upper layers, higher up to the application level to actually provide that. It's not going to be provided by UDP. So looking at the UDP header, you'll see there's much less fields in here. All we have is the source and destination port, the length, and a UDP checksum, and the data. So you can see by comparing the UDP header and the TCP header, there's much less overhead with UDP. Which leads us into where TCP or UDP would be used. Now this is up to the designer of the application. Whenever a designer designs an application, they can choose whether it's going to use TCP or UDP for its transport. They will typically choose to use TCP for traffic which requires reliability. But real-time applications such as voice and video can't afford that extra overhead of TCP, so they would use UDP. Voice and video, it's very sensitive to delay. You've probably watched TV before, you've seen a news report where the newscaster's doing it over a satellite phone, and you can see it's very laggy because satellites are famously high latency connections. So voice and video, it's very sensitive to latency. We don't want to use TCP for real-time traffic like that because the extra overhead is going to slow it down and it's going to affect the quality. So for real-time traffic that's sensitive to delay, we'll usually use UDP. For other applications, we'll use TCP. And because there's a lot more other applications in voice and video, TCP is the most commonly used layer 4 transport. There are some applications that can use both TCP and UDP as well. You'll see an example on the next slide. So here we're going to look at some of the common applications and their destination ports. For applications that use TCP, we've got FTP, the File Transfer Protocol, that uses port 21. Secure Shell is on port 22. Telnet, port 23. HTTP web traffic is on port 80, and HTTPS encrypted web traffic is on port 443. Some UDP protocols, we've got TFTP, the Trivial File Transfer Protocol uses port 69, and SNMP, the Simple Network Management Protocol, uses port 161. And the best known application that can use both TCP and UDP is DNS on port 53. There are some other voice and video signaling protocols that can also use both TCP and UDP as well. Okay, so that was it. That was our layer 4 transport layer lecture. I'll see you in the next one. In this section, we're going to carry on working our way down the OSI reference model. And we've now reached layer 3, so you'll learn about the network layer. We are going to cover the format of the IP header and also the format of IP addresses. You'll learn about the different types of traffic we can have on our network. That's unicast, broadcast, and multicast. And you'll also learn about the subnet mask and about how it defines the boundary between our different subnets. In this lecture, we're going to cover layer 3 of the OSI model, which is the network layer. The network layer is responsible for routing packets to their destination on the network. So this is why routers operate at the network layer, and it's also responsible for quality of service as well. What quality of service is, you might have one particular type of traffic that requires a better level of service than another level of traffic. For example, if you're running voice or video over IP, it's sensitive to delay, so we're going to give it better quality service than something like email. IP, Internet Protocol, is the best known layer 3 protocol. IPv4 is the focus of this section. There is also IPv6 as well, which is the upgrade for IPv4. Later on throughout the course, we'll be talking about About why we have IPv6 and also its actual usage today and how to configure it. IP is a connectionless protocol, so there's no acknowledgements at layer 3. You can still have reliable traffic by using TCP and its acknowledgements at layer 4 or by having it built into the upper layers. Other layer 3 protocols apart from IP include ICMP, which is the Internet Control Message Protocol, which is used for ping for troubleshooting, which we'll also be talking about later in the course, and also IPsec for secure encrypted communications. There are other protocols as well, but IP is the best known one, by far the most commonly used. That's what we're going to be talking about in this entire section. IP addressing is a logical addressing scheme which is implemented at layer 3. So the network designer uses IP addressing to partition the overall network into smaller subnetworks, or commonly called subnets. By having different subnets, it improves performance and security and makes troubleshooting easier. It improves performance because rather than having one big flat network, we divide it into smaller subnets and we can keep the traffic on the particular subnet that it needs to be on rather than going everywhere. So we get better performance that way. We also get better security by having this logical addressing as well. For example, let's say that we've got accounting servers. We can put them on one particular subnet, and that makes it really easy to control who's got access to those servers. Also, it makes troubleshooting easier as well, because by partitioning the network into smaller parts, if we have a problem, it's easy to see what part of the network the problem is on and concentrate there. So that's our layer 3 addressing, uses IP addresses. At layer 2, which we'll get to soon in the next section, we have MAC addresses if we're using Ethernet. IP addresses layer 3, MAC addresses layer 2. IP address is a logical addressing scheme. MAC addresses is just one big flat global addressing scheme. So you'll see this section is going to be a lot longer, more involved than when we get to MAC addresses, because there's a lot more work to do here. There's no logical separation at layer 2 of the OSI model. It's done here at layer 3 with our IP addressing. Okay, this is the first lecture in our layer 3 section. So as usual, we'll have a review of the OSI stack again. You're going to see this several times because it's important, and I really want to drill into you about how networking works. based on the OSI model. So again, we've got the 7 layers. Layer 7 is the application layer. When a sender is going to send traffic, it composes the packet. It creates the layer 7 information first. That then gets encapsulated in the layer 6 presentation layer header, then encapsulated in the session layer header. Top 3 layers are our upper layers, mostly the concern of application developers. As networkers, we start getting really interested at layer 4. So the packet, we've got layer 765, it then gets encapsulated with the layer 4 header, and that will either be a TCP or a UDP header, and the port information will be on there. That then gets further encapsulated in the layer 3 header, which is the subject of this section. Main information in the layer 3 header is the IP address information, but you'll see coming up shortly the rest of the information that's also in the header. Our network infrastructure device that works at layer 3 is our routers. Then we carry on making the packet. We put on the layer 2 header, which is the data link header, on a local area network that will be using Ethernet, and will have the source and destination MAC address there. Our network devices that work at layer 2 are our switches. Finally, the packet will actually get put onto the physical wire, that's at the physical layer, and our hubs work at the physical layer. Not that we still have hubs, we'll talk about that a bit more later too. Okay, last slide in this lecture, we're going to take a look at the IP header. So the top row that you see there, first part is a 4-bit version. It's either going to be IP version 4 or IP version 6. That's referenced in that field. We then have the 4-bit header length, the length of the IP header. It can be a different length because the header options that you see further down can be variable length. We then have the type of service byte. This is used for quality of service information. So we can put a marking on the packet to specify what kind of traffic this is, and on our routers later, we can take an action based on that marking to give it better service if we need to, for example, for our voice over IP traffic. We then have the 16-bit total length of the packet. The next row underneath is used for fragment information. With our different media types, for example, Ethernet, there is a maximum transmission unit size, the maximum size of the packet. Maximum size by default in Ethernet is a 1500 by MTU. If we try to put a packet onto the wire that is larger than that size, it has to get split up into smaller parts, which are called our fragments. The second row of information on the IP header is used to help keep track of those fragments. The next row down, we have an 8-bit time to live field. Every time a packet goes through a router, the router will decrement the TTL field by 1. If it gets down to 0, then that router will drop the packet. What this is for is to prevent routing loops. We might have an error in our network somewhere that is causing packets to endlessly loop around the network without ever getting to their destination. We don't want packets to loop around forever, so TTL will prevent that and drop them. Now, it doesn't fix the underlying problem. We still need to cure the loop so that traffic will actually get there, but it stops us from having a huge amount of traffic getting built up on our network, slowing it down, which is just looping. The next field, the 8-bit protocol, that will specify the layer 4 information type, typically TCP or UDP. We then have a checksum, which is used to check that the packet has not been corrupted in transit. Next, we have the source IP address, specifying where the packet came from, and then the destination IP address, specifying where the packet is going to. The next field is the header options, where we can put in additional information. It's not commonly used. And finally, we have the data, the rest of the packet. Okay, so that is the basics of layer 3 and the IP header, but I've got a lot more information to tell you here, so I'll see you in the next lecture. In this lecture, you're going to learn about the three main types of traffic that we'll send over an IP network, which are unicast, broadcast, and multicast. Unicast traffic goes to a single destination host. Broadcast traffic goes to all hosts on the subnet, and multicast traffic goes to multiple interested hosts. So let's have a look and see how this works. So the first example here is going to be unicast traffic. I've got the sender over on the left, and it sends some particular traffic to the PC up at the top of the picture there, and it also sends some other traffic to the PC up at the top right. So unicast traffic, it's coming from a sender and it's going to one particular host, so unicast. The next traffic type is broadcast traffic. So with broadcast traffic, the sender sends one copy of the traffic that will come into the switch, and then it gets flooded out to all other hosts on that particular part of the network. So you see here it goes to all of the different PCs that are attached to the switch. There's only one copy of the traffic that gets sent everywhere. You'll see it also hits the router in the middle there, which has got an interface which is on that network. What happens then is the router will drop the traffic. So routers do not forward broadcast traffic on. You see the other two interfaces on the router, we don't forward the broadcast traffic out the other side of the router. This is a good thing because if you think about it, like with the internet, imagine if you sent out broadcast traffic and it got sent to everybody on the internet. Well, there's a lot of broadcast traffic, and that would really badly affect performance, and also we could say there's security concerns there as well. So broadcast traffic, one copy gets flooded everywhere throughout that particular part of the network. The next traffic type we're going to cover is multicast, but I want to just mention about how unicast traffic works to multiple hosts first, because this is going to help you understand why we have multicast traffic. So let's say the sender over on the left, it's going to stream out some video traffic, and let's say the bandwidth of the video stream is 1 megabyte. So it sends it to the PC at the top, it also sends it to the PC up at the top right, and it's sending separate copies of the same traffic to each of those individual hosts. It also sends it to the PC over in the middle on the right as well. So we're sending a video stream, it's 1 megabyte in bandwidth, we're sending 3 separate copies of it. So that would take 3 megabytes worth of bandwidth from the host over on the left, also throughout that part of the network as well. With multicast, we send one copy that goes to multiple different destinations. So you'll see how this works. Now the sender sends one copy of that same video stream, and that one copy then gets sent out to all of the interested receivers. So now, rather than sending 3 separate copies, taking up 3 meg in our example, we send one copy, it only takes up 1 meg, so we've got good bandwidth savings there, but it goes to everybody that's interested. The difference between broadcast and multicast traffic is that broadcast traffic goes to everywhere on that particular part of the network, whether the receiver has requested it or not. Multicast goes to multiple receivers, but it's targeted. They have to request it before we're going to actually get it. And a good analogy for multicast traffic is multicast, we send one copy that goes to multiple different destinations. So you'll see how this works. Now the sender sends one copy of that same video stream, and that one copy then gets sent out to all of the interested receivers. So now, rather than sending 3 separate copies, taking up 3 meg in our example, decimal. We send one copy, it only takes up 1 meg, so we've got good bandwidth savings there, but it goes to everybody that's interested. The difference between broadcast and multicast traffic is that broadcast traffic goes to everywhere on that particular part of the network, whether the receiver has requested it or not. Multicast goes to multiple receivers, but it's targeted. They have to request it before we're going to actually get it. And a good analogy for multicast traffic is you can think of it like tuning into a radio station. So all of the different receivers, we've tuned into that. IP addresses are written down in a decimal format, but to understand how they control the logical separation between networks, it really helps if you think about them the same way that a computer does, and that is in binary. So in this lecture, I'm going to show you how to convert decimal numbers into binary, and that's going to help understand IP addressing as we work through the rest of this section. As humans, we're conditioned to count in decimal. It's how we're taught to do it from a really young age, and we do it now without thinking about it. When we write a number down, for each column in the number, we have got 10 possible choices from 0 through to 9. And every time we add a column to the left, the value is multiplied by 10. And we start with ones as the furthest right column. So let me show you what I mean. So when we write down a number, starting from the right-hand side of a number, we've got the ones there. The next column is the tens. Then we've got the ones as the furthest right column. So let me show you what I mean. So when we write down a number, In this lecture, you'll learn about the format of an IPv4 address. And when we write out the IP address, we write it out as a set of 4 octets in a dotted decimal format. So you see an example of an IPv4 address here, 192.168.10.15. Each of those sets of numbers is an octet. So 192 is the first octet, 168 is the second, 10 is the third, and 15 is the fourth octet. IP addresses are written down in a decimal format, but to understand how they Control the logical separation between networks. It really helps if you think about them the same way that a computer does, and that is in binary. So in this lecture, I'm going to show you how to convert decimal numbers into binary, and that's going to help understand IP addressing as we work through the rest of this section. As humans, we're conditioned to count in decimal. It's how we're taught to do it from a really young age, and we do it now without thinking about it. When we write a number down, for each column in the number, we have got 10 possible choices from 0 through to 9. And every time we add a column to the left, the value is multiplied by 10. And we start with ones as the furthest right column. So let me show you what I mean. So when we write down a number, starting from the right-hand side of a number, we've got the ones there. The next column is the tens, then we've got the hundreds, then the thousands, then the 10,000s, and so on. So you can see that it's being multiplied by 10 each time we add a column to the left. If we were going to write down the number 236, the way that we do that is starting from the left now. So starting with the 1000s column, how many 1000s can we fit into 236? Well, obviously that's going to be a 0 because 236 is a smaller number than 1000. So we can't fit any 1000s into 236. That leaves us still with 236 left over. Next up, how many 100s can we fit into 236? Well, we can fit two 100s into 236, and that leaves us with 36 left over. Next up, how many 10s can we fit into the 36 that was left over? We can fit three 10s into 36. That leaves us with 6 left over. And then how many 1s can we fit into 6? That's obviously 6. So that gives us the number of 236 is how we would write that down. Now, like I said at the start of this lecture, that's completely obvious and intuitive to you. So you're maybe wondering why I'm breaking it down like that. Well, it's because binary is not obvious and intuitive, but it works the same way. So seeing how it works with decimal is then going to help understand and see how it works with binary. So computers don't work in decimal, they work in binary. And electrical impulses are either off or on. So there's only two choices, a 0 or a 1, unlike the 10 choices that we have in decimal, which is 0 through to 9. And every time we write down a number in binary, for each column in the number, we've got two possible choices. That's a 0 or a 1, rather than the 0 through to 9 that we had in decimal. And every time we add a column to the left, the value is multiplied by 2, rather than multiplied by 10 as it is in decimal. So looking at the columns in binary now, again, we've got a 1 on the furthest right, the same as it was in decimal. Then we multiply that by 2, so the next is 2. Then we've got 4, then we've got 8. So we just keep multiplying by 2, just doubling it each time. Next would be 16, then 32, then 64, then 128, then 256, then 512, and so on. So you saw how to write down 236 in decimal before. Now let's see how to write 236 in binary. And you can see on the slide here that the number we're going to get in the end is 11101100. So really not intuitive like it is with decimal. But we do it the same way. So rather than seeing how many we can fit in, it's either going to be on or off, 1 or 0. So starting off with 256 here, does 256 fit into 236? Yes or no? Well, no, it doesn't. 236 is a smaller number than 256. So we can fit 0 256s into 236. And that leaves a 6 minus 106 in the 6. You understood that in the 64 binary. I'll pause the like you left, then does 6179 in binary is 1. In this lecture, you'll learn about the format of an IPv4 address. And when we write out the IP address, we write it out as a set of 4 octets in a dotted decimal format. So you see an example of an IPv4 address here, 192.168.10.15. Each of those sets of numbers is an octet. So 192 is the first octet, 168 is the second, 10 is the third, and 15 is the fourth octet. Each octet is 8 bits long. 8 bits, that's why we call it the octet. And if you multiply 8 times 4, that gives you your 32 bits, which makes up the IPv4 address. Okay, first thing I want to do is show you where you can find out the IP address on your different hosts and devices. So let's look in Windows first. So I'll open up a command prompt here. So CMD to open the command prompt, and the Windows command to see your IP address is ipconfig. And I've got a load of output on here because I'm running VMware on my laptop too, so I've got a lot of virtual addresses on here. Let's scroll back a bit until I find my wireless network. This is the one I'm actually connected to my network on, and here, if I mark this, you can see that my IPv4 address is 192.168.1.9. My subnet mask that you'll learn about in the next lecture is 255.255.255.0, so that's also in dotted decimal format. And the default gateway, which is the router that my PC would use to this one, that's 6 in us. I'm going to enter my user v6 address, and address is one that can go there direction. For now, I just want you to get out to a different network, 1.9. My subnet mask that you'll learn about in the next lecture is 255.255.255.0, so that's also in dotted decimal format. And the default gateway, which is the router that my PC would use if it needs to get out to a different network, is at 192.168.1.1. Now, I'm going to tie this all together when we get to the section later, which is called the life of a packet. And in there, I'm going to detail how traffic gets from the source to the destination. For now, I just want you to know that if traffic is going to another host on the same subnet, then it can go there directly. If traffic is going to a host on a different subnet, it has to go there via a router. So you can see my IP address is 192.168.1.9. That's the IP address on my laptop here. The IP address on the router I would use to get out to other networks is at 192.168.1.1. The other information you can see here as well is my IPv6 address, and also the IPv6 default gateway. We'll be talking about IPv6 in a later section. Okay, so in Windows, ipconfig to get that information. Let's have a look on Linux as well. So I'm going to open up an SSH session here to a Linux machine that I've got running, and I'll get the command prompt on Linux. I'm going to enter my username and my password, and then the command to see the IP information on Linux is ifconfig. So ipconfig on Windows, ifconfig for interface on Linux. And you can see here that the IP address on this Linux host is Linux. Finally, figured an IP address on this router yet. Let's just check. The command for that is show IP interface out. And you can see here the default route for my default gateway is 172.23.4.254. Okay, so that's how you get the IP address in Windows and Linux. Finally, let's have a look and see how we get it in Cisco iOS. So I've already got an SSH session open here to a Cisco router. I'm going to enter the command enable to get to the enable prompt so I can see my show commands. And actually, I don't think I've configured. An IP address on this router yet. Let's just check. The command for that is show IP. See, the subnet mask is a /24. The subnet mask can either be written in slash notation or in dotted decimal, and you'll find out about that in the next lecture. With my router, I don't have a default gateway on here, because your router, it's the device that knows about all the different networks, so it doesn't just point at one other router, it's going to have lots of routes in here. You'll find out about routing on the router in other sections a bit further on in the course. Okay, so ipconfig on Windows, ifconfig on Linux, and show interface on our Cisco iOS. It's the same commands for both our routers and our switches. Okay, let's go back to the slides. Next thing to tell you about is static and automatic addressing. On our important devices, like our fixed devices, like our servers, network infrastructure devices like routers, switches, and firewalls, also on our printers, usually we will manually assign the IP. Address on there. For our laptops and our desktop PCs, they'll normally be assigned an IP address automatically through the use of DHCP, which is the Dynamic Host Configuration Protocol. We're going to cover how to set that up later on. The reason that you want your PCs to get their IP address automatically, if you imagine we're in an office with 6,000 people for a large company, you're not going to want to have to go around 6,000 different PCs and configure the IP address manually on all of them. You can centralize that through the use of a DHCP server. It's much more convenient. But for your fixed devices where you want to make sure the IP address is what you think it is and it's never going to change, like on your servers and on your routers, you'll do it manually on them. You're going to have much less servers and routers, so it's not so much hassle to manually set it there. Okay, to understand how the logical separation between our different IP subnets works, you need to understand the IP address in binary. That's Each octet in the IP address has a value ranging from 0 to 255. Let's see how we get that. So it's an octet, there's 8 bits there. Let's count them out. So 1, 2, 3, 4, 5, 6, 7, 8 bits. And it's binary, so the rightmost digit or the rightmost bit is going to be a 1, either a 0 or a 1, and then we're going to double each time we add a bit to the left. So it goes 1, 2, 4, 8, 16, 32, 64, and 128. It's binary, so we multiply by 2, we double each time we go up. And the values are going to range from 0 to 255 for each octet in our IP address. If we put a 0 in on all of those bits, obviously all zeros adds up to 0. If we put a 1 in on each of the bits, if you add these up, 128 plus 64 equals 192, 192 plus 32 equals 204 is 252, 250. I was able to add those up so quickly and it didn't even look like I was thinking about it. Yeah, that's right. When you get more experienced with networking, this is going to be second nature to you. IP addressing is really core to everything that you're going to be doing, so you're going to know IP addressing and its format like the back of your hand, just like I just showed you there. Okay, so that's how we can get the values from 0 to 255. On each of those octets, the bit pattern in here on each of those different bits can be any combination that you want of 1s and O's. It goes from 0 at the lowest value up to 255 at the highest value. The example IP address I gave you earlier was 192.168.10.15. That's in dotted decimal notation. Let's convert that to binary. So the way that you do this is get a piece of paper and a pencil and write out what you see here on the slide. So starting from right and go to left, write out 1, 2, 4, 8, 16, 32, 64, and 128. And then to figure out what your IP address is in binary, start off with the first octet is 192. So we'll do that. And the first thing to do is you start going from left to right. So when you write it out, it's easiest to write it from right to left. But when you're figuring things out, we go from left to right. So the first thing to ask is, can 128 go into 192? Or is 128 equal to or less than 192? And yes, it is. So if that's the case, we put a 1 under the 128. Then what we do is we see what we've got left. Well, 192 minus 128 is 64, so we've got 64 left. We then go to the next column and see, does 64 go into 64? Yes, it does, so we put another 1 in there. We then take the 64 away and we're left with 0. Then does 32 go into 0? Obviously not, so it doesn't go, so we put a 0 there, and it's pretty obvious we've got 0 left, so we're going to have 0 on all of the rest of the columns. So 192, if we were going to write that in binary, it is 11000000. And then to do a final check, to check that we got this right, add these digits together. So add 128 plus 64. When we add them together, it comes up to 192, which is the value we wanted, so we know that we got that right. When you're working this out, if you ever get anything that does not end with a 0 value, you know you've made a mistake, so go back and try it again. Okay, so that was our first octet. Let's do this same process again for the second octet of 168. So does 128 go into 168? Yes, it does. So we'll put a 1 in there. And then the difference between 168 and 128 is 40. We've got 40 left. Does 64 go into 40? No, it doesn't. So we put a 0 in that column. Then does 32 go into 40? Yes, it does. So we put a 1 in there. And then 40 minus 32 gives us 8 left. 16 does not go into 8, so we'll put a 0 in there. 8 does go into 8, so we put a 1 in, and 8 minus 8 gives us 0 left, so we know we can just fill in the rest of the columns with a 0. So 168 in binary is 101010000. And our final check, add the numbers together. 128 plus 32 plus 8 does equal 168. So we got that one right as well. So the first half of our IP address in dotted decimal is 192.168. In binary, it's 110000.101010000. So hopefully you followed along with that okay. What I want you to do now is to stop the video and work out the last 2 octets yourself. So convert 10.15 into binary. And when you've done this, I want you to give me the entire IP address in binary notation. So what your output will be is 110000.10101.000 dot, and then the next octet in binary, and then another dot, and then the final octet in binary. So go ahead, stop the video now, and we'll check your answer in a second. Your 128. Eight plus 32 plus 8, 10101.000 dot, and then the next octet. So the first octet was 11000000. 128 plus 64 equals 192. The next octet of 168 was 10101.000. 128 plus 32 plus 8 equals 168. The next octet, you should have got 00001010. 8 plus 2 equals 10. And then the last octet of 15, you should have got 00001111. 8 plus 4 plus 2 plus 1 equals 15. If you look at the top of the slide here, that should have been your final output. That is the complete IP address. In binary. Hopefully you found that really simple. With just a tiny bit of practice, you'll be able to do this without hardly even really thinking about it. Okay, so that's how we figure out the IP address to set the boundary between our logical networks, our subnets. The IP address is in this lecture, you're going to learn about subnet masks. And you can see what I've done here is I've opened up a command prompt on my Windows laptop again, and I've entered ipconfig, and you can see where I've highlighted it that my IP address is 192.168.10.15. My subnet mask is 255.255.255.0, and the default gateway is 192.168.10.1. So every host in your network is going to know what its IP address, its subnet mask, and its default gateway is. Let's now see how it's going to use that information. So onto the slides now. A host can send traffic directly to another host on the same subnet via the switches that they're attached to. But for a host to send traffic to another host in a different subnet, it must be forwarded by a router. So our routers are our devices that link our different subnets together and route the traffic between them. The host, therefore, needs to understand if the destination is on the same or a different subnet in order to know how to send it. If the destination is on the same subnet, it will send it there directly. If it's on a different subnet, it knows that it has to send it to the local router, which is the default gateway. And the way that the host knows whether the destination is on the same subnet or a different subnet is by comparing the IP address of the destination to its own IP address and subnet mask. The subnet mask, just like the IP address, is also 32 bits long, and it can be written in dotted decimal notation, the same as our IP addresses, or it can be written in slash notation. You'll see how that works a bit later in this lecture. A host's IP address is divided into a network portion and a host portion, and it's the subnet mask that defines where the boundary is between the network part and the host part of the address. And the easiest way to explain how this works is by giving you an example. So let's say the host's IP address is 192.168.10.15 and the subnet mask is 255.255.255.0. That's the IP address and subnet mask that's actually on my laptop. To figure this out, we write the IP address out in binary notation, like you learned in the last lecture, and then the subnet mask also in binary notation underneath. So our example was 192.168. Like you learned in the last lecture, and then the subnet mask also in binary notation underneath. So our example was 192.168.10.15, subnet mask 255.255.255.0. So you see the top part here, I've written 192.168.10.15 out in binary, and then underneath 255.255.255.0 out in binary as well. The IP address is compared or masked with the subnet mask. A 1 in the subnet mask indicates that bit in the IP address is part of the network address, and a 0 indicates that the bit is part of the host.
Okay. So I'm just going to write down the basic binary. Well, what we need really. What you need to know, or you need to have, or you need to basically know in order to kind of like do binary. Like once you know these, you can understand binaries really fast. So let's go like this. All right, so So it's 128 and 64, 32, 16, 8, 4, 2, and 1. I remember this like when I was in school was probably like just that 1 times 2, 2 times 2, 4 times 2, 8 times 2, blah, 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 and that. And now this is basically what you will use, to get any binaries, really. Binary cheat. Okay. Yeah, I just wanted a reason to stand up and write something. Oh no. Basically, we just wrote the binary cheat over here. Right over here. So we have it for when we are trying to count binaries. But yeah, that was all.
Host address. So very quickly you can see here all the ones on the subnet mask go up to here. Everything in the IP address above that is part of the network portion of the address. The zeros above that in the IP address, those are part of the host portion of the address. Let's make this a little bit clearer. So subnet mask 255.255.255.0. With the subnet mask, it's always going to have contiguous ones, and you see the ones come up to this part here. So I put a line in. That line is the border between the network portion and the host portion of the address. So in the example, the network address portion is 192.168. Because on the IP address from here on the left all the way up to the line, that is 192.168.10 part of the IP address. Whatever is after the line is the host portion of the address. So in our example, it is the .15 is the host portion of the address. And I've highlighted it there. There is the network portion. If the host wants to communicate with another host with an IP address, which
of course
also begins
I kind of
with
understand about it, kind of like in my
192.168.10
own
in our
way,
example.
basically.
So say for example that this.
So in a way that I understand it, it's like it's basically, maybe it's the way that it is, but let's say we're like on a device, right? We can set up multiple IP addresses for multiple devices, but the last part, the last portion, that little portion, that's the host address of that address. So what I'm trying to say is like that last part cannot be the same on every devices. Hopefully I'm correct. Okay, that's it. That's all I wanted to add. Okay. I understand it now. Okay, so basically, the whole point, and this is just my thoughts, but like the whole point of subnetting is to kind of know slash understand we need to use if we need to send the traffic via a router or not. So if it's sending to a device on the network that has the same IP address as it, like not the same IP address, but like it starts the same way, but like at the end, like the host is a little bit different, like, you know, 192.168.10.20, it knows that you can just send it directly, traffic directly, since they are all on the same network or on the same IP address. But if he needs to send it to a different one that's like on that 11.20, he has to send it via a router. All
Host
right.
wants to send traffic to a destination address of 192.168.10.20, it knows it's on the same subnet and it can send the traffic directly, because the destination also begins with 192.168.10.
I'm just gonna write this just so my future self doesn't cut his head off.
If this host wants to communicate with another host on any other network, anything that does not begin with 192.168.10, then it knows it has to send the traffic via a router. So if it was sending traffic to destination 192.168.11.20, for example, it doesn't begin with 192.168.10, it's a different subnet, sends it via the router.
Yeah.
For a destination address to be on the same subnet, the network portion has to be exactly 192.168. Anything else means it's a different subnet, we have to go via a router. The subnet mask always begins with a contiguous block of ones.
So it has to have the 1111111. Okay.
This is different than the IP address. You see our example IP address here, it's 11000000.
Like IP address is free to do whatever you want between
with the IP address, the
255, like
ones and the
between
zeros
0
can
and
be mixed
255.
about in pretty
But
much any order. The
subnet must
subnet
start
mask
with
is a block of ones
255.
and then a block of zeros, always. We never mix the ones and the zeros up with each other in the subnet mask. So 1111.1111.1111.0000.000, etc. is a leak and must be unique. Printers, router interface. 0101, mixing up the ones and zeros, we can't do that. That is not a valid subnet mask.
Yep.
The host portion of the address is available to be allocated to the different hosts on that particular subnet. For example, your PCs, servers, printers, router interfaces, switch management addresses, etc. With two exceptions that you'll see coming up after the next slide. So there's the host portion of the address for our example highlighted. The host portion of the address specifies the individual host and must be unique on that subnet. Your hosts do not need to be numbered sequentially. For example, we could have a subnet with two hosts on it. One could have address 10.10.10.10, the other could have address 10.10.10.20. We don't need to number them .1 and .2. You can't have two different hosts both with the same IP address. For example, we couldn't have two hosts both with address 10.10.10.10. That would be a duplicate address. And whenever any traffic was sent to 10.10.10.10, your network devices wouldn't know which host to send it to. So that's illegal. You can't have duplicate IP addresses. You could have host 10.10.10.10 on one subnet and host 10.10.20.10 on a different subnet. They're different subnets, so it's not a duplicate address. That's just fine. which host to send it to. So that's illegal. You can't have duplicate IP addresses. You could have host 10.10.10.10 on one subnet and host 10.10.20.10 on a different subnet. They're different subnets, so it's not a duplicate address. That's just fine. All zeros in the host
I'm
portion.
about to be here with copyright claims. Ugh.
Designates the network address and is not allowed to be allocated to a host. Remember, we just said a minute ago that there's two particular addresses that cannot be assigned to a host. The first one of those is all zeros in the host portion. That designates the network address. For example, we couldn't have two hosts both with address 10.10.10.10. That would be a duplicate address. And whenever any traffic was sent to 10.10.10.10, your network devices wouldn't know which host to send it to. So that's illegal. You can't have duplicate IP addresses. You could have host 10.10.10.10 on one subnet and host 10.10.20.10 on a different subnet. They're different subnets, so it's not a duplicate address. That's just fine. All zeros in the host portion designates the network address and is not allowed to be allocated to a host. Remember, we just said a minute ago that there's two particular addresses that cannot be assigned to a host. The first one of those is all zeros in the host portion. That designates the network address or the network ID. In our example, the network address would be 192.168.10.0. So we fill in the bit pattern in the network portion. So that was 192.168.10. And then in the host portion, we put all zeros in there. So all zeros, you can't assign it to a host. It signifies the network address, which is the bottom address in that particular subnet. And there's it highlighted there. You can see we've used all zeros. The other address which cannot be assigned to a host is all ones in the host portion of the address. So all zeros signifies the network address, which is the bottom address in the range. All ones, which is the top address in the range, that is the network address, which is the bottom address in the range. All ones, which is the top address in the range, that is the directed broadcast. Whenever zeros. The other address which cannot be assigned to a host is all ones in the host portion of the address. So all zeros signifies the network address, which is the bottom address in the range.
So all zero network address.
All ones, which is the top address in.
Okay. All zero, aka 1, 2, 3, 4, 5, 6, 7, 8 is for network address. I know I keep on repeating myself, like I'm repeating myself literally, but it's for a purpose. It's a thick head. Okay. All right. And all ones, like 1, 2, 3, 4, 5, 6. Is it 6? 1, 2, 3, 4, 5, 6, 7, 8. 6, 7, 8 is for
in the range. That is the directed broadcast. Whenever you send traffic to the directed broadcast address,
and this is all applied to the last numbers. So like the last 1 1.
it goes to all hosts in that subnet, not to an individual host. So we can't assign that address to an individual host.
Yeah.
And there it is highlighted, the host portion.
So not valid. This not valid. Okay. All right. Let me just write that down. You know what I'm saying? Invalid IP address example. So 192.168.10.0. What's it? Address. All right.
And I've put all ones in there. So that leaves 192.168.10.1 to 192.168.10.254 in our example available to be allocated to our different hosts. So all
So the only valid ones will be from from 1. So I was just gonna do as an example, it'd be valid, and I don't know why I have to write these, but valid IP address would be like x dot x dot x dot 1 to x dot x dot x dot 254. All right, that's all right. Understandable, comprehensible.
all the different PCs, other kinds of hosts. Maybe we've got some Windows PCs, some Linux PCs in that subnet. I can number them from 192.168.10.1.
Sounds like this one football commentator.
10.254. They're all in the same subnet. Whenever they send traffic to each other, they can do that directly without going via their default gateway router. Okay, we can also write the subnet mask in slash notation. 255.255.2. .255.0 is writing it in decimal notation. So the example here, 255.255.255.0, we can write that out, the subnet mask, and you see there is the line between the network portion and the host portion. Okay, we can also write the subnet mask in slash notation. 255.255.255.0 is writing it in decimal notation. So the example here, 255.255.255.0, we can write that out, the subnet mask, and you see there is the line.
Okay, so because the subnet mask always begins with contiguous ones, it will be 1 to 32 bits long, counting from left to right. This allows us to write the subnet mask in slash notation, which is more convenient than dotted decimal for network diagrams or in conversation.
Line between the network portion and the host portion. And as we covered earlier, it's always contiguous ones and then followed by a block of contiguous zeros. Because it's contiguous, we can count how many ones that we have in a row. So the example here, we have got 24 ones in a row. I know that each of these blocks is an octet, they each equal 8. So that's 8,
Oh,
16,
okay. I guess
24.
that's what you mean. So, okay. Like, we can say we have 24 ones in a row.
So 255.255.255.0, we can write it like that in dotted decimal notation. Another way we can write it is /24. Those two things both mean
A row or slash 24.
exactly the same thing. If we had 255.255.0.0 as a subnet mask, we could write that as /16 and so on. And whenever you configure a Cisco router or switch on iOS,
Oh, okay. So that's why, just a little note on my, for me really. That's why you can write an IPv4 address like this. Even IPv6, I believe, think. Well, IPv4 like this. 192.168.10.15/24. Gotcha. Okay. Oh, where did our music go? Okay, they're still here. Let's just, let me just remove this comment and leave this here because I need that.
when you configure the IP address and the subnet mask, you have to write the subnet mask out in the full dotted decimal notation. But whenever we're having a conversation with somebody, or if we're creating a network diagram, more commonly we will use slash notation because it's not much fun to be saying 255.255.255.0 all the time.
Yeah.
It's much easier to say /24.
True.
Also, /24 takes up much less space on your network diagrams, so you can have your diagrams looking a lot neater and tidier. Okay, there was the network portion for a /.
Oh, look at me. My gosh. I just took a breath. Release.
24 highlighted. Let's look at another example coming up. Again, we're looking at the /24 there. So the other example is for IP address 10.10.10.15 /255.0.0.0. And hopefully you can just, by looking at this, you're going to see that that's going to be a /8. The more you get used to working with IP addresses and subnets, you'll very quickly be able to see where the lines are by just looking at the actual address and mask. So the example there, the IP address can be written as 10.10.10.15 space 255.0.0.0 or 10.10.10.15/8 when we're writing it out in full with the subnet mask. In the example here, the network address is 10.0.0.0/8. I've put this in bold to highlight it because the network address is not 10.10.10.0/8. When we write this out, it's just the network portion of the address that we specify. So it's a /8, so it's only the first octet, which is the network portion, so that is the 10. All the rest of the address, the last 3 octets, is the host portion. So when we write this address, it would be 10.0.0.0/8. And the available addresses would be 10.0.0.1 for our first host. The last host would be 10.255.255.254. We can't use 10.255.255.255 because that would be the broadcast address, and 10.0.0.0 is the network address. Okay, that was everything I needed to tell you about the subnet mask for now, but we'll be covering it in more and more detail as we go through the rest of this section.
Oh, come on. What's more to there to subnet, man? What's more? Bruh, networking be doing too much. Networking be doing too much. Oh. Uh, I'm lost. I am out of it, brother. I am out of it, brother. Been at it for more than 7 hours now. More than 7 whole hours. Ta-da-da. Even our music stopped. And I forgot about it. I did not hear of that. Did anybody hear of classes? I didn't. I didn't. I didn't. Oh, I didn't. I do not know. IPv4/24, I guess. Correct? Okay, a Class C subnet is usually. I did not know. All I know is just /24 is all. It's mostly. I do not remember that. Not one bit. So I'm just gonna put it in host portion subnet / notation. Okay. I'm just gonna put it somewhere here. I'm gonna put it here. A Class C subnet is usually 255.255.255.0 or /24. A Class C, we're in a / notation for a IPv4 Class C network subnet. Whatever. Next. Okay, why issue arises when two devices on network given the same address? IP conflicts. Yeah. So if you have 44 and are converting to binary, which value fits entirely into the remainder after placing a 32? After placing a 32, so 44 minus 32, that's 1, 2. So I will say 8. Oh no. Oh no. Yeah, because 16 will not. No, it will not. A remainder of 4. Yeah, whatever that is. Okay. It will not fit. Okay, what happens when a packet is sent to a directed broadcast address on a subnet, ignored by all, delivered to specific host, sent to all hosts on the. Oh, what happened when a packet is sent to directed broadcast? Broadcast. It just goes to everyone. It goes. No, it sends to all hosts on the subnet. Yeah, it just sends it to everyone. There is more about subnetting. Brother, really? Are these people serious? How much of subnetting is needed to be known? How much of it is needed? Like how much? How big is subnetting, man? This is how you know you don't know nothing. Well, you can't always know everything, can you? All right, so we're done with that. Network layer. Was a lot. Not gonna lie, it was a lot. It was a lot. Network layer. Okay, we're done with module 6. Now module 7. 1, 2, 3, 4. Notice that I only have like 4 modules because I don't like the welcoming. I don't need that. I don't need that. I just need these ones. And I've done this when I was back in high school. Not high school. When I was back in college. I had a class for this, but I just did it just to pass the class. But I understood a lot because I liked the class and I knew how important it was for me. So I was able to do my best. But yeah, at the end of the day, it was still a class. So I ended up forgetting most of the stuff, which is this.
In the last section, we covered the format of an IP address. In this section, you'll learn about the different address classes. So we're going to go through class A, B, C, D, and E.
So
this information
those
is important to
why was I asked
understand
about
before
those
we get into the
classes,
more
about
advanced
classes
topic
in the
of
previous
subnetting,
one
which
when
we're
you
going to do in
introduced
the
them
next
in this
section.
one? Coursera. Maybe he mentioned it somewhere when I wasn't even paying attention. But it was not on none of the flashcards.
In this lecture, you'll learn about the IP address classes. We're going to cover classes A, B, and C here, which are used for allocating addresses to our hosts. And then in the next lecture, we'll cover classes D and E. Okay, the first thing to talk about is the effect that line
I think this is where, I think this is where I would need to
which
actually pay a lot
designates
of
where the
attention.
network portion of the address is and the host portion of the address. If a subnet mask is a /8, for example, using the first 8 bits for the network portion of the address, then 8 bits for the network portion, 24 bits for the host portion. If we compare that with a
I will need that to be explained
/24,
a lot
we're going to
more.
have 24 bits for the network portion and only 8 bits for the host portion. So we could have a /8 is going to have not many networks but a lot of hosts per network, or a /24 would have a lot of networks but not many hosts per network. So we've got a trade-off whenever we decide where that line is going to be about how many networks we're going to have and how many hosts that we're going to have. Okay, let's talk about how internet addressing was originally supposed to work. Because when IPv4...
No, I still do not understand. Okay, so the global coordination of internet IPv4 addressing is performed by I spent a lot of freaking time just learning which organizations these were, like when I was in class, because they always asked about those organizations. I hated, like, I did not remember any of them. But there was like the I IAS or something, IIN. I hated it.
Everybody would be using it, and that everybody would require an IP address. So when they first designed it, they designed it for what was right at that time. And as we go through this section, you need to think about the internet, about how it was then, to understand why IPv4 was designed the way that it is. There's a few issues with IPv4 that you'll learn about as we're going through this section, and those issues came about because the designers didn't realize what was going to happen in future. So as long as you think about it from that point of view, then everything should make sense. So the original way that IPv4 addressing was meant to work, when a company wanted to communicate on the internet, they would apply for a range of IP addresses. Now, the global assignment of IP addresses is handled by IANA. That stands for the Internet Assigned Numbers Authority. So they are up at the top level looking at it from a global point of view. They assign large blocks of addresses to the local authorities in different regions. So a company, they would apply to their local authority to get a range of public IP addresses. If they had 6,000 hosts, for example, they would ask for a range of IP addresses big enough to cover that, plus some room for growth in the future as well. That company would then allocate those addresses to their hosts in their different offices. Unfortunately, when IPv4 was created, the designers didn't realize how big the internet was going to get, like we were just saying, so they didn't create a big enough address space. There's not enough IPv4 addresses for every host that actually needs an IPv4 address that's going to be communicating on the internet. So IPv4 ran out of addresses. The long-term solution for the problem is IPv6, which has got a much bigger address space. IPv4 is a 32-bit address, IPv6 is a 128-bit address, and we're going to be talking about IPv6 in a lot of detail in a later section. Private IP addresses with NAT, which is Network Address Translation, are, however, currently deployed in the majority of enterprise networks as a workaround. So IPv6 is the long-term solution, but today, private addresses with NAT is actually more commonly deployed. But as time goes on, there will be more uptake of IPv6. Again, we're going to discuss private addresses, NAT, and IPv6 in a lot more detail as we go through the course. But as I was saying, to understand the next few lectures, don't think about private addressing, NAT, and IPv6 yet. We're going to get to there later. To understand why we have those and how they work, you need to understand the original implementation first, so that's what we're going to cover first. So Class A addresses. The Internet authorities split the global IPv4 address space into separate classes. Class A addresses are assigned to networks with a very large number of hosts. So Class A, there's going to be a small network portion and a large host portion. The high order bit, which is the first bit in a Class A address, is always set to 0. And if you look down in the bottom left at the address there, you see I've highlighted the first bit. It's always going to be a 0 in a Class A address. With Class A addresses, the default subnet mask is a /8, so 255.0.0.0, and valid network addresses range from 1.0.0.0 to 126.0.0.0/8. So that's the network address. The actual host address ranges from 1.0.0.1 to 126.255.255.254. So 1 to 126, that allows for 126 networks. And if you counted up the host bits, 2 to the power of 24 adds up to 16,777,214 hosts per network. Now, you maybe noticed adds up to 16,777,214 hosts per network. Now, you maybe noticed there, if you actually counted this up, the available values, if you set the first bit as 0, that allows for 126 networks, and if you counted up the host bits, 2 to the power of 24 adds up to 16,777,214 hosts per network. Now, you maybe noticed there, if you actually counted this up, the available values, if you set the first bit as 0, would actually be, we could have all zeros, and we could go up to 127. But all zeros and 127 are not in the valid address range that we can assign to our hosts, because they are reserved addresses. 0.0.0.0/8 is reserved and signifies this network, and it's used by some protocols. So 0.0.0.1 to 0.255.255.255 are not valid addresses that you can assign to hosts. That entire range is not available. Also, 127.0.0.0/8, which is also in the Class A space, is also reserved. That is used as the loopback address, and it's used for testing the IP stack on the local computer. So 127.0.0.1 to 127.255.255.255 are not valid host addresses. So you see I've written down at the bottom here, whoops, they just wiped out over 33 million addresses that could have been used for addressing actual hosts on the public internet. If you think about it, this network, they could have just used a single address for that, like one address rather than 16 million addresses. And the same for the loopback, they didn't really need 16 million addresses to be used for loopback testing. And if you're thinking, well, there's this huge shortage of addresses on the internet, why would they do something crazy like that? But the reason is, when IPv4 was designed, they didn't realize that they were going to run out of addresses. So they thought, hey, it's no problem, we can assign 16 million addresses for testing. It doesn't matter because we don't have a shortage of addresses. They didn't realize what was going to happen later on. In fact, let me give you a demo of using the loopback. So let me open up a command prompt here on my laptop, and if I did an IP config, again, I've got loads of virtual adapters on here, but if I scroll up slowly, you'll see I don't have the IP address 127.0.0.1 assigned to any of my network cards in here. It's built in with IP. So I can ping 127.0.0.1, which is the loopback address, and you see I'm getting a reply, which means it's up. The reason you do this is to test that TCP IP is working on the local machine. If you wanted to check, say that you're in New York and you want to check that you've got connectivity to a server in Boston, you could ping that server. There's not much point in pinging the server in Boston if you can't get to your local default gateway router in New York, so you would ping that first. And also, there's not much point in pinging the local router if TCP IP isn't even working on your laptop. So the way that you verify that TCP IP is up and running on your laptop is by pinging the loopback, and we can ping 127.0.0.1. But like I was just saying, it's the entire Class A range, beginning with 127, that is actually reserved for testing loopback. So I don't have to ping 127.0.0.1. I could ping 127.100.200.50, and this is going to work as well. So I can ping anything beginning with 127, and it's going to check the local TCP IP stack. So it's good to have that address for testing, not so good that they took out an entire Class A network for it. Okay, so you see that all zeros would begin with 0, obviously, and 127 is 0 and then all ones. Class A always begins with a 0 as the first bit. Okay, now, obviously, a company that had a Class A address would not put all 16 million hosts into a single logical network. That would be terrible for performance and security. They would split that big /8 range up into smaller subnets and assign those to their different departments in their different offices. For example, if they received the Class A address 15.0.0.0/8, they could allocate the subnet 15.0.1.0/24 to sales computers in New York, 15.0.2.0 255.255.255.0 to accounting, that was just the same /24 in dotted decimal notation, and 15.0.9.0/24 to sales computers in Boston. So they would have that huge network that they got assigned by the internet authorities, and they would split it up into smaller subnets that they could assign to their different offices and their different types of hosts in different offices. And when you do that, it's called subnetting. You're going to master subnetting in a later lecture because it's super important. Okay, we covered the Class A addresses. Next up is Class B. So Class B addresses were originally assigned to medium to Large-sized networks. With Class B, it's the first 2 bits in the address are always going to be set to 10. Class A addresses default to a /8, which is the first octet. Class B subnet masks always default to a /16, which is the first 2 octets. And the valid network addresses range from 128.0.0.0 to 191.255.0.0. Again, this is a Class B. The subnet mask is the first 2 octets, so the ranges use the first 2 octets. So 128.0 to 191.255. That allows for 16,384 networks and 65,534 hosts on each of those networks. Again, you would never have a flat subnet with up to 65,000 hosts in there. If you were given a Class B network in the real world, again, you would subnet it into smaller subnets. The last class that we'll cover here, the last one that can be used to assign addresses to hosts, is is Class C, and this is used for small networks. You saw that Class A, we've got the first octet, so /8 is used for the subnet mask. Class B, the second octet, it's a /16, and with Class C, the default subnet mask is a /24 up to the end of the third octet. And with Class C, it's the first 3 bits that are important. They're always set to binary 110. The valid network addresses range from 192.0 to 223.255.255.0. That allows for a little over 2 million networks and 254 hosts per network. That's something that you're going to know by heart later on. A Class C network has got 254 hosts up to that amount. With a Class C, that's small enough that that could be allocated as is for a real world deployment, or again, if we wanted to, we could actually subnet that into smaller networks as well. A quick note on private addresses now. So I gave you all the addresses that were available in our Class A, B, and C networks, and we spoke about the reserved addresses for our loopbacks, and also the addresses beginning with 0 are reserved as well. There's also a range of reserved private addresses in each class. Those are valid to be quick note on as is for a real world deployment, or again, if we wanted to, we could actually subnet that into smaller networks. With a Class C, that's small enough that that could be allocated as is for a real world deployment, or again, if we wanted to, we could actually subnet that into smaller networks as well. A quick note on private addresses now. So I gave you all the addresses that were available in our Class A, B, and C. networks, and we spoke about the reserved addresses for our loopbacks, and also the addresses beginning with 0 are reserved as well. There's also a range of reserved private addresses in each class. Those are valid to be assigned to hosts, unlike the other reserved addresses, but the difference is that these ones are not routable on the public internet. So these were originally designed for hosts in a closed private network that should have no internet connectivity. For example, imagine you've got a high school and you've got students there that need to work on PCs, but you don't want them to be able to browse the internet. You would put them on private addresses. The benefits you get from that are that they can't get hacked because they're not connected to the internet, and also it doesn't cost you anything. You have to pay for public IP addresses. Private IP addresses are, of course, free. The different ranges that are used for our private addresses: in Class A, it's 10.0.0.0 to 10.255.255.255 on the host addresses. The private host addresses in Class B, 172.16.0.0 to 172.31.255.255, and the Class C private range, 192.168.0.0 to 192.168.255.255. Again, when you're experienced with working in networking, these are things that you're going to know off the top of your head. Private addresses, there's quite a bit more we need to talk about with those. That's going to be covered in a later lecture in this section. Okay, so that was all the info I needed to give you about our Class A, B, and C classes for now. We'll talk about the Class D and Class E addresses in the next lecture. In this lecture, you're going to learn about the other address classes, that's Class D and Class E. So you saw in the last lecture that classes A, B, and C include all all the addresses that are valid to be assigned to our end hosts. And those addresses went up from a 1 in the first octet up to 223. But you're maybe thinking, what about 224.0.0.0 to 255.255.255.255? Because you know that the maximum value in each of our octets is 255, we only went up to 223. Well, the next class is class D, and class D is used for multicast addresses. You'll learn about what multicast is right on the next slide. With class D, the 4 high order bits, the first 4 bits in the first octet, are always set to the binary value of 1110. We can actually count this up. If you look at the first octet down in the bottom left here, we've assigned the bits 1110. A class D always begins like that. So if we add these up, 128 plus 64 plus 32 is 224. So the lowest address is going to be 224. And then the remaining bits over to the right are 8, 4, 2, and 1. If we add those up, it adds up to 15. And 224 plus 15 adds up to 239. So that's where we get the range of 224 to 239 from. So the lowest address is going to be 224, and then the remaining bits over to the right are 8, 4, 2, and 1. If we add those up, it adds up to 15. And 224 plus 15 adds up to 239. So that's where we get the range of 224 to 239 from. These class D addresses were not allocated to hosts, and there's no default subnet mask. They're used just for multicast traffic. So to see how not allocated to hosts, and there's no default subnet mask. They're used just for multicast traffic. So to see how multicast works, let's do a quick review of unicast first. I've got my sender over on the left, which has got the source IP address 10.10.10.10, and it's going to send traffic to destinations at 10.10.10.15 and 10.10.20.15. So it sends traffic to 10.10.10.15, and if you looked in the packet in the layer 3 IP header, you would see the source IP address is 10.10.10.10, the destination is 10.10.10.15. And if we're using a /24 subnet mask, they're both in the same subnet, so that traffic can go directly between the hosts without having to go via a router. Let's say that the host then sends traffic to the other host up in the top right. Let's say that this is a video stream that we're sending again. So we've unicast it to 10.10.10.15. We then unicast it to 10.10.20.15 as well. If you look in the IP header, again, unicast traffic, the source address is 10.10.10.10, the destination address is 10.10.20.15. Again, we were using that /24 subnet mask, so they're on different networks, so the traffic is going to have to go via a router. And if this was video streaming we were doing here, it's two completely separate pieces of traffic, so it's going to use 2 meg if it was 1 meg per stream. Now, we can improve this by using multicast traffic. With multicast traffic, we're going to send one copy of the traffic from 10.10.10.10, and that one copy is going to get sent to 10.10.10.15 and 10.10.20.15 as well. We're going to run an application on the sender, which is going to send it as multicast traffic, and in our example, we're going to send it to a destination multicast address of 239.0.0.1. It still comes from the same source address of 10.10.10.10, and the destinations still have their normal unicast addresses there as well, but we send it to this special multicast address. That will then go to all of the hosts that were interested in getting that traffic. A good analogy of this is you can think of it like tuning into a radio station. So on most hosts, 10.10.10.15 and 10.10.20.15, they ran an application on there that said they wanted to receive the stream for 239.0.0.1. As long as you've configured support for this on your routers, that traffic will get forwarded to all of the hosts that are interested in receiving it. And the benefit you get is, example here, we're only sending 1 meg's worth of bandwidth rather than 2 meg. And if there was 50 interested hosts, it would still just be 1 meg worth of bandwidth rather than 50 meg. So you save a lot on the bandwidth that you're using. It makes things a lot more efficient. Moving on to Class E addresses, they are experimental and reserved for future use. The first bits in a Class E are always set to 1111. So again, if we count it up, that's going to give us the possible values of of 240.0.0.0 to 255.255.255.255. Just like our Class D multicast addresses, these addresses do not have a default subnet mask. There is one special address that is actually used in Class E, which is the broadcast address of 255.255.255.255. That is the broadcast address for this network, meaning whatever network the source is on, it's a broadcast for that network. Actually, while we're talking about broadcast traffic, let's just go back to the previous slide for a minute, and I'll explain further about why multicast is different and can be more efficient than broadcast traffic. Notice in the example here, on the local subnet, the hosts that are attached to the switch, it only went to the top host at 10.10.10.15. The traffic did not get sent down to the host below that at the bottom. If this was broadcast traffic, it would be sent to all hosts on that subnet, not just the ones that wanted it. So multicast is more targeted, it's more efficient. Another difference is that as long as you've configured your routers to support it, routers will forward multicast traffic. So that's how we were able to get it to the host up in the top right. Broadcast traffic does not go outside its own local subnet. It does not get forwarded by routers by default. Okay, so that was our Class D and our Class E addresses. These Class E reserved addresses, they are never really used. You need to know what they are, and particularly for the CCNA exam, but real world, you'll never come across Class E addresses. They're not used in production environments. Class D addresses are used if you're using multicast. Okay, so that was our Class D and our Class E addresses. Let's just have a look at a summary of the different classes before we move on. So
Oh my gosh. Last time I did this was 5 hours ago, or maybe 3 hours ago. Oof. Alright, so we need to write something on the dashboard. I haven't done streaming like this in a while. It was this long. Alright, so here's the summary for our classes. IP classes. Alright. We can basically just leave them here too. IP address classes. Okay, so we have class A, B, C, D, and E. Okay, here we have first octet, which will be 1 to 126. I could make this much more smaller. Did I have to make it like that? Class A, class B will, that's still large. Class B will be from 128 to 196 to 191. 128 to 191. Class C, that will be, class C will be 192 to 223. then class D will be 224 to 239, and then class E will be 240 to 255. This is experiment only. Okay, experiment only. All right, so the slash, this will be /8 /16, I believe. Yeah, and /24. No, I wonder why. Oof. And it's 255.0.0.0. 255.255.0.0. 255.255.255.0. And these are the slash pattern. I don't know what that is. Slash, and these are the dotted decimal, and they are all default subnets. Default subnet mask. Okay, so my question is, and always has been, how do we know which octet? Huh? So how do we come up to that? Okay, so 18 /8 /20 /24. I wanted to have that. There was a better example that I wrote down, like here, yeah. Like class A is 10 that to like. No, I haven't wrote it better. I can write much better than this. Okay. All right, so just down here. Okay, so IP address classes. Okay, so we have a class, first octet, and then we have subnet mask, which will be slash method and the decimal. Okay. All right. First class A, this is 1 to 126, and then it's class B, that's 128, yep, to 191. Then class C is 192 to 277, 223, and class D is 224, again to 239. and then class E would be 220, 240 to 255. This one doesn't matter that much, so yeah. In slash, that would be 8, that would be 16, that would be 24. In decimal, that would be 255.0.0.0, and this would be 255.255.0.0, and this is 255.255.255.0. Okay, now I'm going to add my other examples. So class A, that will be from 10 dot, yeah, so it's 10.0.0.0 to 10.255. Okay, and then class B, it will be 172 dot 162 dot 0. Yep, that makes sense. To 172 dot 31. I don't know why that 2.5. I don't know if those are just examples. Oh, those are the private. Yeah, these are private IDs. Okay. Then class C, we have 192 dot 168 dot 0.02, 192 dot 168 dot 255 dot 255, and these are the private IP addresses. Okay. All right, I'm a little bit satisfied. I am satisfied a little bit. It hasn't explained everything yet. It does not explain everything yet, but I am satisfied with that.
Class A is 12126 in the first octet. The default subnet mask is a /8. Class B is 128 to 191, and that defaults to a /16. Class C is 192 to 223, and that defaults to a /255. You want to have these classes committed to memory, not just for the CCNA exam where they're completely essential, they're also completely essential for real-world networking as well. Okay, that's it. See you in the next lecture.
let's uh let's I was looking at class B. That would be from that would be this one up here. It would be this one and not that one. Well, I wasn't even thinking about it anyways. So yeah. All right. So what's the primary purpose of subnetting? What is the primary subnetting? Let me see. Assign reserve address to each host. Create multiple points of access. Encouraging faster IP. Divide network into smaller, manageable sections. Yes, that's the point of it. How many hosts can a Class C network host? Class C 254? No, it's 128, right? Ah, well, looks like it's up to. I forgot. 255? I don't know. Oh, maybe I do know. I don't know. All I know is that 255 is just not, it's used for something else. Okay. So let me go back to C. Default mask that. Yeah. This allows 200 hosts. Okay. So let me see hosts. Let me add that section back. For class C, that's 200. More about class B and wow, class B has a lot. Yeah, for 65,000. 65,534. And class A, I think it was yeah, it's I think it's the small, not the smaller one. It's bigger than class B. But yeah, about 6,000. Medium. It hosts 6,000. And class C is probably what most people uses. From what I can understand, is what most people use, like what most in-house devices use. Identify the valid range for class B IP address. 128. Yes, it is. I can't. What is the purpose of 127.0.0.0 IP range? Provide multicast, test IP. Yep, it's just to test. All right. It seems like I just like getting 80% on this. I mean, if I can pass it, that's okay. I don't need to try again, We can just go,
In the last section,
one.
we started off on
Oh,
OSI
my
Layer 3,
head is-
and you learned about IP addresses and how we can combine
need to
those with the
rest.
subnet mask
I need to rest.
define the boundaries between our logical networks. In this section, we're still going to be on Layer 3, but we're going to go much deeper into how we can control the boundaries between our networks with the use of subnetting. Now, if you've heard about this already, you've maybe heard it's one of the more complicated sections to learn for CCNA, but don't worry, we're going to go through it step by step. I'm going to show you loads of examples. I'm going to get you to work through examples as well, and by the time we're done, you're going to have this down.
Bro, it's a lot. It's a lot. It's a lot, man. It's a lot. Not gonna lie to you. It's a lot. It's a lot. It's a lot. It's a lot.
This is a short lecture where you're going to learn about CIDR, which is classless inter-domain routing. A problem with the
Out of energy. All right.
implementation of the classful addresses was that when the Internet Authorities gave out addresses, they always gave out a complete class A with a /8 or a complete class B with a /16 or a complete class C with a /24 subnet mask. And this gave a problem that if a company had more than 254 hosts, they were too big for a class C, they would have to be given a class B. And if they had, say, 500 hosts, they would actually get allocated addresses for 65,534 hosts. So that's obviously way too much, and this led to huge amounts of the global address space being wasted. So CIDR, classless inter-domain routing, was introduced in 1993 as the solution or a partial solution for that problem. So CIDR removed the fixed /8, /16 and /24 requirements for the different address classes. And allowed them to be split into smaller networks. And the name for this is subnetting. Again, we're going to be talking about subnetting a lot in the later lectures as well. So, for example, the Internet Authorities could allocate the address 175.10.10.0/20. You can see from the first octet, 175, that that is a Class B address, which would normally be a 16, but rather than allocating the organization the entire 16, the Internet authorities could now assign them a /20, which meant that other networks in that 175 range would be available to give to other companies. So rather than giving out the huge range, we split the classes into smaller networks that could be given to different organizations, and meant that there would be less addresses getting wasted. So companies can now be allocated an address range that matches what they actually need and doesn't waste extra addresses. We get another benefit from CIDR as well, which is route summarization. You see in the example here, we've got ISP-A, and they have allocated the address blocks that you see on the left. So one company got 175.10.0.0/24, another one got 175.10.1/24, 175.10.2/24, etc., all the way up to 175.10.255.0/24. So they've given out 255. Address blocks there. We've also got ISP-B, and they've given out 175.11.0, 175.11.1, and so on, again /24s, all the way up to 175.11.255. And ISP-A and ISP-B get connected. Now, if we didn't have CIDR and we weren't able to do route summarization, ISP-A would advertise, it's actually 256 address blocks there, they would advertise all 256 address blocks to ISP-B, and ISP-B would vice versa advertise all their 256 address blocks to ISP-A. But when we've got CIDR and route summarization, what we can do is the two ISPs can advertise just an aggregate block. So ISP-A, rather than advertising all 256/24s, it advertises 175.10.0.0/16, which is a superset of all those 256 smaller networks. So now ISP-B, it only learns one route to all the networks behind ISP-A rather than learning 256. And ISP-B will vice versa just advertise one route of 175.11/16 to ISP-A. So the benefits we get from this is that ISP-A doesn't know about all 256 networks behind B, it only gets a single summary route that covers all of them. Obviously, if it's got one route rather than 256 routes, that's a lot less information, it's more efficient, it takes up less memory in the router.
Okay, break time.
Welcome to my complete CCNA, Cisco Certified Network Associate course. This is Jeremy's IT Lab. Welcome to my complete CCNA, Cisco.
All right, we're back. Let's finish this before it hits 10 hours.
This is a short lecture where you're going to learn about CIDR, which is classless inter-domain routing. A problem with the original implementation of the classful addresses was that when the internet authorities gave out addresses, they always gave out a complete class A with a /8 or a complete class B with a /16 or a complete class C with a /24 subnet mask. And this gave the problem that if a company had more than 254 hosts, they were too big for a class C, they would have to be given a class B. And if they had, say, 500 hosts, they would actually get allocated addresses for 65,534 hosts. So that's obviously way too much, and this led to huge amounts of the global address space being wasted. So CIDR, classless interdomain routing, was introduced in 1993 as the solution or partial solution for that problem. So CIDR removed the fixed /8, /16 and /24 requirements for the different address classes and allowed them to be split into smaller networks. And the name for this is subnetting. Again, we're going to be talking about subnetting a lot in the later lectures as well. So, for example, the Internet authorities could allocate the address 175.10.10.0/20. You can see from the first octet, 175, that is a Class B address, which would normally be a 16, but rather than allocating the organization the entire 16, the Internet authorities could now assign them a /20, which meant that other networks in that 175 range would be available to give to other companies. So rather than giving out the huge range, we split the classes into smaller networks that could be given to different organizations and meant that there would be less addresses getting wasted. So companies can now be allocated an address range that matches what they actually need and doesn't waste extra addresses. We get another benefit from CIDR as well, which is route summarization. You see in the example here, we've got ISP-A, and they have allocated the address blocks that you see on the left. So one company got 175.10.0.0/24, another one got 175.10.1/24, 175.10.2/24, etc., all the way up to 175.10.255.0/24. So they've given out 255 address blocks there. We've also got ISP-B, and they've given out 175.11.0, 175.11.1, and so on, again /24s, all the way up to 175.11.255. And ISP-A and ISP-B get connected. Now, if we didn't have CIDR and we weren't able to do route summarization, ISP-A would advertise, it's actually 256 address blocks there, they would advertise all 256 address blocks to ISP-B, and ISP-B would vice versa advertise all their 256 address blocks to ISP-A. But when we've got CIDR and route summarization, what we can do is the two ISPs can advertise just an aggregate block. So ISP-A, rather than advertising all 256/24s, it advertises 175.10.0.0/16, which is a superset of all those 256 smaller networks. So now ISP-B, it only learns one route to all the networks behind ISP-A rather than learning 256. And ISP-B will vice versa just advertise one route of 175.11/16 to ISP-A. So the benefits we get from this is that ISP-A doesn't know about all 256 networks behind B, it only gets a single summary route that covers all of them. Obviously, if it's got one route rather than 256 routes, that's a lot less information, it's more efficient, it takes up less memory in the router. And if an individual link goes down in ISP-B, it doesn't have any impact on ISP-A because that one summary route doesn't change. It's going to be different in ISP-B. Whenever one of their routes goes down, the other routers are going to have to recalculate that. But the benefit we get from this is we're compartmentalizing the different parts of our network. And if we've got an issue in part A of the network, it's not going to impact part B of the network. So it makes things a lot more stable and reliable, makes things more logical, which is better for us humans as well, because it makes it easier to troubleshoot them. Okay, that was CIDR, which is closely related to VLSM, our variable length subnet masks. We'll be getting to that real soon too. See you in the next lecture.
Cisco Certified Network Associate course. This is Jeremy's IT Lab.
And so on, again, /24s, all the way up to 175.11.255. block. So ISP-A doesn't know about all 2B 11/16 to ISP-B. It only gets a single summary route that covers all of them. Obviously, if it's got one route rather than 256 routes, that's a lot less information, it's more efficient, it takes up less memory in the router. And if an individual link goes down in ISP-B, it doesn't have any impact on ISP-A because that one summary route doesn't change. It's going to be different in ISP-B. Whenever one of their routes goes down, the other routers are going to have to recalculate that. But the benefit we get from this is we're compartmentalizing the different parts of our network. And if we've got an issue in part A of the network, it's not going to impact part B of the network. So it makes things a lot more stable and reliable, makes things more logical, which is better for us humans as well, because it makes it easier to troubleshoot them. Okay, that was CIDR, which is closely related to VLSM, our variable length subnet masks. We'll be getting to that real soon too. See you in the next lecture. At the end of this lecture, you're going to understand how we can implement subnetting. Now, I'm actually going to cover subnetting over a few lectures in this section. Subnetting is a really important topic, not just for passing the CCNA exam, but for networking in general. It's really one of the core knowledge areas that you need to understand if you're going to work in networking. So if you need it, take a quick break before you watch this lecture, then get yourself a cup of coffee and come back, and we're going to dive deep into network. Okay, to understand this lecture, you need to think about it from the context of the originally intended IPv4 design, just like we did in the previous few lectures there, where all hosts which can communicate on the internet have a public IP address. Now, if you're already working in a company where you've already got exposure to working on the network, the chances are that your company is going to be using private IP addresses. Now, as we go through these lectures, do not think about it from that point of view. Okay, we're going to get into private IP addresses later, and I'll also explain how modern day networks work. But before we get there, you need to understand how IPv4 worked in the first place. It's a natural progression. Understand this first, and then you'll be able to understand why we use private addresses on our networks and how they work as well. Okay, so just bear with me and think about it from the point of view of how the internet worked like 10 or 15 years ago, before we were running out of addresses and before everybody was using private addresses. Oh, while I say that, by the way, the majority of companies are using private addresses, but there are a few out there that are using public addresses everywhere. That is pretty rare though. Okay, so for our example, let's say that we're a network designer for a small business with 4 departments that are spread over 2 offices, and we want to manage our own public address space. So what we could do is we could buy 4 separate Class C networks for that. But the problem is that public IP addresses cost money. So rather than doing that, rather than buying separate networks from the internet authorities, we could purchase a single range and subnet it into smaller portions. Like, let's say we've only got a handful of hosts in each of those departments. Rather than buying 256 addresses for each, we can buy a single Class C range, and then we can divide that network up into smaller networks and assign it to the different parts of our networks. So in the example, let's say we've got that Class C range, and it is 200.15.10.0/24, the default Class C subnet masks. So to do our subnetting, to divide that network into smaller subnets, we need to borrow some host bits and add them to the network portion of the address. So we're going to move the line that separates the network portion of the address and the host portion further over to the right. So we're going to take some of our host addresses away and give them to the network portion of the address. When we do subnetting, the line always moves to the right. And the further to the right we go, the more subnets that we're going to have, but the less the amount of hosts that we'll have on each subnet. To calculate the number of available subnets that we're going to get by moving the line to the right, we use a formula of 2 to the power of subnet bits. Now, the first time I saw this, I thought, oh, I don't know how to do to the power of, never really covered that in school much. Don't worry, it's super simple, as you'll see as we go through these next few lectures. So if a Class C network uses a /28 subnet mask, then we've borrowed 4 bits from the default of 24. Okay, normal class C mask is a /24. If we change that to a /28, the difference between 24 and 28 is 4. The way we calculate how many subnets we're going to get by doing that is it's 2 times 2 to the power of the amount of subnet bits that we borrowed. So we borrowed 4 bits for the network portion from the host portion. To see how many networks we're going to get, it's 2 to the power of 4. To calculate this, it's dead easy. You can do it on your fingers. You start off with 2 and you just double. So I go 2, 4, 8, 16. I'm going to now have 16 available subnets. Another example, if a Class B network uses the same /28 subnet mask, well, the default for a Class B is /16. So if we subnet that to a /28, we've borrowed 12 bits. To see how many subnets we're going to get, it is going to be 2 to the power of 12. So let's do this one. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096 subnets. For that one, you might have noticed it's easy if you remember that 2 to the power of 10 is 1024. Here we just keep doubling each time. And remember that hosts on different subnets need to go via a router if they want to communicate with each other. That's the whole point of having our IP addressing and of doing subnetting. It's to divide our network up into different logical parts of the network, and it's the routers that are the device that know how to get everywhere and that can direct the traffic. Okay, so that was how to calculate the number of subnets we're going to get. It's 2 to the power of how many bits that we borrowed. To calculate the number of hosts, know how to get everywhere and that can direct the traffic. Okay, so that was how to calculate the number of subnets we're going to get. It's 2 to the power of how many bits that we borrowed. To calculate the the number of hosts, it's 2 to the power of how many host bits there are minus 2. We need to subtract 2 because we've got the network address and the broadcast address that cannot be assigned to hosts. That's the 2 that we take away. So if a Class C network uses a /28 subnet mask, then we've got 4 bits left for hosts. There's 32 bits in the address. If we're using 28 for the network portion, that leaves 4 for the host portion. 2 to the power of 4 is 2, 4, 8, 16, minus 2 for the network address and the broadcast address. That means that we would have 14 available addresses for our hosts. If we've got a Class B network and it's using a /28, again, we've got 4 bits left for our hosts. So 2, 4, 8, 16 minus 2 is 14. It's exactly the same. So notice that the amount of hosts we're going to get is going to be dependent on the subnet size, and it's going to be the subnet mask size. It's going to be the same whether it's Class A, Class B, or Class C. But the amount of subnets we'll get, if I go back a slide, it's going to be different for Class A, B, or C because they've got different default subnet mask sizes. For example, if we use a /28 with a Class B, then we're going to have 4,096 available subnets. If we use a /28 with a Class C, we're going to have 16 available subnets. There's a difference there. But for the hosts, it's always going to be the same. Okay, a quick note on IP subnet 0 command. Just like we have to subtract 2 to get the number of valid hosts, back in the day, we used to also have to subtract 2 from the number of available networks. This is because in the original internet standards, it wasn't allowed to use network bits of all zeros or all ones, just like we can't use host bits of all zeros or all ones. So that took away 2 of our available subnets. However, there wasn't really any practical need for that, and it wasted address space. There is a practical need with the host bits because we've got that network address and the broadcast address that are actually used, but as far as the number of subnets go, we were taking away 2, not really for any good reason. So on Cisco routers now, for quite a long time, there's a default command of IP subnet 0, which disables that behavior. The command is enabled by default, so those 2 extra network addresses are available in Cisco networks. It's important that I tell you this because you might look up something on the internet, you might look up a subnet calculator there, and it will tell you that there are 14 networks available on a Class C with a /28, for example, when I'm telling you that there's 16. Okay, with Cisco networks and for the CCNA exam, do not take 2 away from the number of available subnets. Okay, and I want to tell you that just so you don't get confused if you're looking up anything on the internet. Okay, moving on, let's say that we've been allocated Class C 200.15.10.0/24, again the same as the last example, and here we're going to move the line all the way to the right. We're going to go with a /31. Obviously we can't do a /32 if we want to have more than one available host now. You can use a /32 subnet mask, but there's only one host there. That's mostly used for loopback addresses. Don't worry about it yet, we're going to talk about that later on. So if you do need to have multiple hosts, then the furthest right you can go is a /31. If we wrote that subnet mask in dotted decimal notation, it would be 255.255.255.254. We get the 254 because it's 128 plus 64, 32, 16, 8, 4 plus 2 comes up to 254. So that leaves 1 bit for the host address, which has obviously got a possible value of a 1 or a 0. So a class see a /31, it borrows 7 bits for the network address from the host address. That gives us 128 subnets, which is 2 to the power of 7. Again, let's count it up. 2, 4, 8, 16, 32, 64, 128. And that's going to accommodate 2 hosts each. So that's what we get with a /31. 4, 8, 16, 30. 64, 128, and that's going to accommodate 2 hosts each. So that's what we get with a /31. The valid host addresses would be 200.15.10.0 to .1, 200.15.10.2 to .3, then 200.15.10.4 to .5, etc., all the way up to 200.15.10.254 and 255. You can check this by, we're using 200.15.10, so the first 3 octets are never going to change. The last octet, you just start with all zeros, and then it would be 0000001, and then a 0 or a 1, and then 0000010, and then a 0 or a 1, and so on. Okay, but wait, if we're using a /31, there's only two possible values to assign to hosts. What about the network and broadcast address? Yeah, a /31 subnet breaks the standard rules of IP addressing, where we have to have the network address and the broadcast address at the top and the bottom of the range. /31 subnets are, however, supported on Cisco routers for point-to-point links. If you think about it, a point-to-point link, there's just one side and the other side. Well, any traffic that comes from here needs to go to the other side and vice versa. There's nowhere else for it to go, so there isn't really any point in having a network and a broadcast address. So that's why Cisco allowed that exception. You can have a /31 on a point-to-point link. Okay, next up, moving on, we're going to move the line back a space. We're going to create a /30 now. The subnet mask in dotted decimal, 255.255.255.252, that and /30, they both mean the same thing. That is going to leave 2 bits for the host address, because we got 2 bits for the host address. 2 to the power of 2 is 4, minus 2 for the network and the broadcast address. That gives us 2 possible hosts. It borrows 6 bits for the network address. If we count this up, 2, 4, 8, 16, 32, 64 is our 64 bits, which can accommodate
I will not lie to y'all. My brain is fried. My brain is fried. I cannot think. All I can do is just write at this point. That's all I can do right now. I cannot think for myself right now. Like all I'm just hearing is just blah 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 right now. So I'm gonna end this session right here right now. Oh my gosh, we're so close to 8 hours. 10 hours. I'm too tired. I can't take any more of this subnetting. Nope. I cannot. For me, to me, it sounds like just yappa 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 yappa. You know, understanding, huh? I don't understand. I wasn't understanding before, but now it's like it's just the yappa yappa yappa. I don't know if it's because it's getting harder or just I'm sleepy. It's 6 and I've been on this chair for like 10 hours now, so that makes sense, but my gosh. Okay, so they recommend, or what they're saying is, after this one, you then take this one, which I will actually start. I'm already enrolled in it. Okay, that's good. And it's this one that I'm doing. I knew what it was. I knew it was this one. Okay, so and then next one will probably be intermediates, which is switching, VLANs, and routing. So let me go. Foundation network basics. I've already done this. It's supposed to take 8 hours. Foundations. Aren't I here? Look at me. This is why I'm telling you, like, I cannot think right now. I cannot think. I'm just going around in a corner, like just like that, in a corner. But we know that our next one is this one, which is 10 hours, course 2, which is 10 hours, and it is intermediate. All right, we're going to enroll. Okay, let's get started on this one. Let's just drop some of them down. Okay, let's just drop some of them. For the last minutes that we have, I cannot focus. I cannot read. So I'm just gonna have to take some notes. Introduction to Cisco Intermediate. That was module 1. Well, it's not module, it's course. Course 1. It was called Conclusion of the CCNA Basic Network Fundamentals. It is for network fundamentals. Basically, it's basically just network fundamentals, but it's that. Now we're on course 2, CCNA Intermediate Switching and VLAN. Okay. So I was thinking of just copying this overview. I don't need it to be here. All right. Let me just start with my notes. Let's just start it. Let's just start with the notes, man. We can do over. Thank you. Looks like we might need that overview back. Well, I can have key commands, and I can have overview down here. Okay, overview. So this one has 9 modules. Okay, down there. None over there. It can be down there. So we can 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, I know there's a way to probably do this. There's probably a better way to do this, but I'm an old soul. What can I say? Just preparing ourselves for tomorrow. Since today it's like we're basically just done for today. There's no point in me 1, 2, 3, 4, 5, 6. I've tried. I'm trying, but I think I know that better than anyone else that I'm at my end right now. I'm at my maximum. I need my rest. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now module 1, which will be OSI layer 2, the data. Hold up. What's this? Huh? Rephrasing. Nah, bro. Yeah. I forgot I could do that. I mean, I've been trying not to copy and paste a lot. I mean, like basically writing it. Writing is basically copy and paste, but at least in writing, you are at least, remembering what you're writing. At least you're kind of like getting, oh, I wrote that. I remember writing that. I remember my hand hurting when I was writing that. The Cisco troubleshooting methodology. I should probably be doing this and that. Yeah. Okay. I should have done that. Cisco device management. I wonder if I could just jump modules. I want to be able to do that, but then I also have the mentality of saying like, oh my gosh, what if there's something that, you could always learn something. There's always something new to learn. So I was like, what if there's something in this book or in this course that I could have learned? Know what I'm saying? So I'll put in this. Okay. Routing, troubleshooting methodology. All right. Life of a packet. Device function. Physical layer. Data link layer. Okay. There we go. All right. I'm sure 10 hours have already, passed, but I'm still gonna okay, so in this module, explore OSI layer 2, also known as the data link layer, which ensures a reliable data transfer between devices within the same network. We will delve into Ethernet technology, its role in networking, and how it supports seamless communication. The physical layer. Okay, so after this, I will probably have to rearrange the things a little bit. I will like put the layers nodes together and things like that. Targets learner, ideal for CCNA candidates, network engineers, IT professionals, basic networking, blah blah blah. Learning objective, implement layer tool, switching and learning trunking, implements troubleshooting, filling, routing, configure and troubleshoots. Okay, learning objective. There we go. That's this. I don't have I don't have questions to revisit, but I would love if you can turn this into an H3. Okay. All right. How about we just do a little bit of note taking? Save ourselves sometimes for tomorrow. All right. Complete that. For specialized resources. CCNA packet publishing. All right, I'll have to look back and find my GitHub account. I don't know where you want, but looks like advanced deep learning with Keras, Python, unlocking hands-on automated testing with Playwright, software architect with .NET, mastering Docker on Windows. Hold up. Hold up. Are you telling me you're just gonna have all the chapters here, or do you just have its cheat sheet? Okay, the resource and link provides supporting files. Okay, it's just supporting files. I'll be surprised if that was for free.
We're going to carry on working our way down the layers of the OSI reference model in this section. In the previous section, we covered layer 3, the network layer. In
Yeah.
this section, it's layer 2, the data link layer. And we're going to focus
Network layer
specifically on
stupid.
Ethernet, which is the layer 2 medium, which is used on local area networks. We're going to talk about wide area network layer 2 mediums.
I prefer
later
the
on
physical
in the
layer.
course. We're going to talk about the format of the Ethernet header, and you'll also
Module
learn
2
about
doesn't seem
the
to be
makeup
long.
of the MAC
Module
address.
9, of course, it's the longest. Module 8 is alright. Module 7 is alright. Module 6 it's alright.
this
Module
lecture,
5
you'll
is
learn
alright.
about layer
Module 4.
2 of the
I feel like I'll be
OSI
able to
reference
finish
model,
this much
which
more
is
earlier.
the data link layer. Layer 2 frames are encoded and decoded into bits, ready to put on.
Alright. That is good, and that is enough for today, guys. Oh, future me, if you're watching this, remember you still gotta do this. I'm still gonna come back and do this tomorrow. That's what I'm going to start with. But for 10 hours today, we were able to do most of this. And most of the time we spent setting up, looking up, getting used to the way of how we're going to be doing this. So tomorrow is we're just going to jump in tomorrow. We're just jumping straight in. Finish that. Let me look at my grades. Yeah, all 60%. I mean 80%. So that's all right. I mean, if I could also get 80% on here, 80% on here, that's all right. I would like that actually. All right, there, and then we'll come and do this tomorrow. So we are on track with your 5-day learning plan this week. So we have 5 days left. Tomorrow. Oh my gosh. Okay, so it will be tomorrow. So it's going to end next Tuesday. That's a lot of days. Tomorrow we're going to do this course too. I have a feeling that there's a course that's gonna have to take us about 2 days. I have a feeling about that. The advanced one, yeah. I feel like the advanced one will take us some days to get used to it. Oh my gosh, it will. 2 days. So if I can finish that tomorrow, and then on Friday and Thursday, I will just focus on this one. Friday and Thursday, I will focus on this one. And the point is, like, I haven't even made an appointment for the CCNA, but my point is here is to learn these things as quick as I can, and then have like all my notes, having everything. And then after that, not even after that, during that, where after the trial has ended, I will continue learning them. I will continue practicing them with a packet tracer. I will buy my own stuff and set up my own, servers, and set them up like professionally. Professionally. And then I will go and take the test, because I want to do it on the first time. On the first trial, that's when I want to do it and hit at the first trial. I don't want to, take trials here and there. My gosh. Wow, 48. 1 hour is 2 hour, 1 hour, 1 hour, 1 hour, 1 hour, 1 hour. Spanning tree protocol, hot stand router protocol, ether channel, switch chat, security, access control lists. Oh my gosh. Now what? Okay, and then the last one is the experts. Of course, after that, I've already be good. So, device security, network device management, quality of service, cloud computing. I have a cloud computing book, so I could go into that after that. Wireless networking, network automation. Are they gonna do Python? Of course. Of course, it's gonna be Python. I was literally just thinking of like, what if I just jump into this? The problem with this is I could just jump into this, right? And I could do it much faster. But the thing is that I won't be able to connect stuff in my brain. As a matter of fact, I might in this module we'll explore essential, including security, encrypting password and configuring authentication from like AAA. Yeah, if I feel like I'm unable to do it in 7 days, I will jump to this and finish it. Because the only hard one, really, the only hard one will be okay. So if that is done today, next up is the intermediate, and then advanced, and then expert. So the only one is going to be the advanced. So this is done today, but tomorrow, and then at the same time going to be done with the intermediate tomorrow, and that would leave us with 4 days, and then we'll take those 2 days to do the advanced one, and then that starts with the other 2 days, and the other 2 days will be for the expert and overview for everything else. All right, that's the plan. That's the plan. Okay, all right, I'm done. Y'all probably done, so I'm gonna go eat, go to sleep, read some books, and be done with the day. It was a good day. I love it. Peace out, y'all.